was dedicated to the 3 doctoral candidates who have already obtained their degree, let's say, in the field of other natural hazards than earthquake engineering, than seismic hazard. Whereas now we will thus be focusing on the ROSE curriculum, actually the one that gave birth to this seminar. There are 4 candidates. 3 of them will be defending their thesis, whereas the 4th has already done so in another university because he's part of a co-tutel program, so you will not be seeing questions from the jury, very likely to the 4th candidate. This is the reason for that. So I just wanted to explain that before. And now I would first like to thank the 3 members of the evaluating committee that came from Trento, from Naples, and from Pisa to help us in assessing the very high quality, I must say already, of these 4 doctoral students. So Professor Walter Salvatore from Pisa, Professor Ivan Giongo from Trento, and Dr. Maria Teresa De Risi from Naples. So thank you very much for your presence here. Thank you also for the family members, for the friends of the candidates. And okay, I will stop here. I will now give the word to the candidates. Let's go to what matters. And we will start with Niccolò Damiani. So Niccolò will be presenting his research regarding the seismic performance of framed retrofit solutions for unreinforced masonry buildings.
Divided into 2 main parts, besides the introductory and conclusive section, that are related to the 2 different retrofit solutions that I had the possibility to study during my PhD. And both the retrofits will be addressed following a similar approach, so starting with an introduction to the solution, and then moving to a summary of the performance that they exhibited in dedicated experimental testing, and in the end, I will introduce some analytical and numerical tools that were developed based on the available data. In most of the developed countries around the world, a major part of the existing building stock has reached the end of its design lifespan. Indeed, referring, for example, to Europe, almost the 75% of the existing building stock has been recognized to be energy inefficient. And considering that the substitution of the existing building stock with a new one would not be sustainable from the environmental point of view, the best solution is then represented by the lifetime extension of existing buildings. And besides energy upgrading, let's say, requirements that are becoming more and more important considering our historical period, the recent earthquake, as those occurred in Southern Europe, demonstrated the inadequate seismic performance of existing buildings, which experienced severe damage or even collapsed, causing severe economic and human life losses. Therefore, the lifetime extension of existing buildings should include, besides their energy upgrading, also their seismic improvement, raising, therefore, the interest on integrated retrofit solution. Today, I will focus on unreinforced masonry, that has been one of the most popular building materials since the dawn of civilization until today. And although masonry is progressively losing its popularity, there is still a large number of unreinforced buildings around the world. And moreover, these buildings were built before any seismic and energy efficiency regulation. And as a result, all these buildings built before 1990s often require retrofitting intervention. Moreover, urine buildings are also widespread in low seismicity regions where recent events demonstrated how natural phenomena or anthropogenic activities, like, for example, gas extraction, can result in ground shakings with an intensity higher than expected, and striking, therefore, buildings designed only for vertical loads. Within this context, the objective of my research was the study of the structural and seismic behavior of 2 innovative retrofit solutions for unreinforced masonry structures. And both the retrofits rely on retrofit frames made of different materials and connected to the masonry internal or external surface. And both the retrofits were conceived as comprehensive retrofit solutions, so able to overcome the main deficiencies exhibited by masonry buildings. Indeed, they mainly aim at improving the in-plane capacity of masonry members, but enhancing also the building's structural integrity. The retrofit were also conceived as a modern retrofit solution, so able to fulfill, let's say, modern requirements such as sustainability, lightweight, cost-effectiveness, and ease of installation. Moving then to the first retrofit solution, it was a multi-component retrofit based on timber members. And it consisted in timber frames that are connected to the masonry internal surface and coupled with nailed oriented strand boards. This solution was conceived within the NAM project, which was an extensive research project aimed at studying the seismic vulnerability of the existing building stock of the Groningen region of the Netherlands, which was subjected in last year to induced seismicity. The retrofit stems from an out-of-plane strengthening solution already proposed in literature to prevent the out-of-plane failure of walls, and this solution has been extended to improve also the in-plane capacity of piers. Indeed, as you can notice here from this slide, a flexural contribution is provided by the vertical timber post and by their connection, while a contribution to the shear strength is provided by the OSB sheeting. It is interesting to notice that since the OSB is applied directly to the timber frame below, the retrofit behavior is then governed by the nails employed to connect the OSB to the timber frames. Then, the retrofit that is connected to the masonry and to the floors aim also at preventing the onset of local mechanism, favoring a building global box type response. Then, before moving to the description of the numerical and analytical tools, I want only to present a small, let's say, summary of the performed experimental testing that were already described last year by my colleague Marco Miglietta, with whom I collaborated during the experimental campaign. So the retrofit effects were firstly investigated through in-plane quasi-static cyclic tests, which were performed on nominally identical piers in both bare and retrofitted configurations. And although the retrofit, because of its reduced stiffness if compared to the masonry, was not able to delay the onset of damage or modifying the initial pier stiffness, it allowed a good strength increase of 35% and a significant ultimate displacement increase of 167%. The tested pier represented the first-story longest resisting pier of a full-scale building specimen, which was the subject of the next step of the dedicated experimental campaign. So moving to the next step, it consisted in dynamic shake table tests, which were performed also in this case on two nominally identical full-scale building prototypes in bare and retrofitted configurations. And the specimen represented a terrace house, which is a widespread structural typology in the Netherlands, and recognized to be significantly vulnerable to seismic actions. The structural system relied on a two-story cavity wall system with an inner load-bearing calcium silicate leaf and an external clay veneer, and as you can see summarized here, a combination of structural details was selected to maximize the prototype seismic vulnerability. Moving to the retrofit intervention, the same layout that was previously tested was then tailored and applied to the building specimen. And as you can notice, differently from the longitudinal sides that were characterized by large openings, no OSB sheeting was applied on the transverse side that were actually solid walls, aware of their already significant in-plane capacity. The retrofit intervention included also the strengthening and stiffening of the second floor timber diaphragm. The specimens were then subjected to a unidirectional shake table test along their longitudinal direction using an input signal representative of induced seismicity, which was scaled up to the building near collapse conditions. And as you can see summarized here, the bare building was able to sustain a PGA of 0.4 G before attaining its near collapse condition, which were reached because of the poor connection between the second floor diaphragm and the masonry piers. That triggered a local sliding mechanism that concentrated therefore the damage and the displacement demand at the second floor, preventing a global response. On the other side, thanks to the improved connections provided by the retrofitted building was able to prevent the onset of this mechanism, favoring a global box type response. And as a result, the retrofitted building was able to sustain a PGA of 0.8 G before attaining its near collapse condition that were reached with this damage concentrated this time at the first floor with the full exploitation of pier capacities. Then, starting and based on this experimental data, the focus moved on the development of numerical models able to account for both the contribution of the masonry and of the retrofit solution. To do so, we employed the software Tremuri, which is based on nonlinear macro elements in an equivalent frame approach. And as you can see, the retrofit was modeled by means of trusses elements. In particular, vertical trusses represented the contribution of the timber post and of their connections, while two pairs of diagonal trusses represented the equivalent contribution of the OSB sheeting. The strategy was first verified against the in-plane quasi-static test, and as you can see, you can notice a fair match between the numerical results and the experimental responses, with a tendency of the numerical model to overestimate the dissipated energy. The modeling strategy was then applied to the full-scale building specimen, and here I want to specify that the equivalent frame formulation that is available in Tremori account for the in-plane behavior of walls and diaphragm. And although cavity wall buildings are recognized to be vulnerable to out-of-plane loading, actually, for this dimension of the prototype, for this specific case study, experimental evidences demonstrated that the damaged states of the buildings were not reached because of the out-of-plane failure of walls, enabling, therefore, the possibility of, let's say, a simplified modeling strategy. Here you can see the different damage states and the damage limits that are defined as the threshold between the different damage states that were considered in the analysis of both experimental and numerical results. Moving to the numerical simulation of the shake table test, you can see here the results obtained for both the bare building and for the retrofitted one. And overall, the numerical models were able to adequately simulate the response of the building at least up to damage limit 3. Then, for different reasons, the employed modeling was not able to, let's say, simulate the significant flexibility showed by the experimental prototypes. Indeed, in the first case, as expected, the local mechanism that appeared at the second floor was not possible with this modeling strategy to capture the entire evolution of this mechanism, and so to simulate this large displacement at the second floor. On the other side, looking on the retrofitted building, this one was a video but is not playing, but actually the significant damage that the prototype, the retrofitted building, exhibited at the first story actually was characterized by a vertical crack between longitudinal and transverse walls, actually causing a very significant loss of stiffness and therefore large displacement at the first story that cannot be accounted for using an equivalent frame formulation. Overall, considering that the model were fairly good, represented a fairly good approximation of the experimental results, was possible to study the seismic behavior and response of different retrofit levels. This topic is of particular interest given the multi-component nature of the system, which allow to design the building seismic performance balancing structural and economic goals. To do so, starting from the experimental scheme that are represented here as scheme 0 and scheme 2, two additional schemes were actually interpolated from the configuration tested in the experiments, where scheme 1 is actually the lightest retrofit solution with only vertical timber post, while scheme 3 represents the heaviest retrofit solution with the OSB sheeting applied on all the building sides. Then, for each retrofit scheme, nonlinear time history analyses were performed using a database of 250 ground motions representative of induced seismicity. The results are summarized here, and they are then post-processed, and fragility curves were derived for each retrofit scheme and for each of the 4 damage limits. Looking at the numerical results, it can be appreciated how, looking at the first damage limit, that is DL1, so immediate occupancy, the retrofit did not provide a significant improvement of the building performance as expected because of its reduced stiffness if compared to the building, to the mesorelief. And however, it can be observed that eventual OSB sheeting may cover eventual airline cracks formed at this stage. Therefore, so other comments can be done about this topic. However, moving to damage limit 2 and to damage limit 3, that are immediate damage mitigation and life safety, you can see how the performance of the retrofit was significant, but no significant difference were denoted by the different retrofit scheme, suggested that for this level of performance, the lightest scheme, the scheme 1, should be the optimal solution. Looking instead at damage limit 4, that are near collapse condition, you can see how a significant improvement of the building performance can be obtained by selecting a scheme that could be scheme 2 or scheme 3, depending on the target performance objectives. Starting then from the gain knowledge about this retrofit solution coming from both experimental and numerical evidences, analytical formulations were developed for the retrofit design and response prediction. I want to point out that these formulations are not empirical, but are based on simple, let's say, mechanics, and therefore a preliminary version of this equation was already conceived before the experimental testing to allow a correct design of the retrofit. And then the formulation were, let's say, updated and organized in terms of a step-by-step design procedure to assist engineers in real practical retrofit design applications. So the first step is represented by the design of the retrofit against out-of-plane loading, so with a formulation proposed for the definition of the seismic force demands, and also for the design of all the components involved in the out-of-plane response. The next step was then represented by the retrofit design against the in-plane loading, so also in this case with formulation proposed to control and to assess the flexural and shear contribution provided by the retrofit, as well as for the design of the connection and of the involved retrofit components. As a final step, we propose also a simplified procedure for the design of a retrofit intervention in case of flexible diaphragms. Unfortunately, today I have not a lot of time to go into the details about this formulation. However, these formulations were then conceived and then validated against the available data coming from the experimental test that I presented before. Here you can see a short list of the publication or research work that has been published about my work on the timber-based retrofit solution, and then we can move to the second retrofit solution. That was a modular that rely on modular steel frames that are connected this time to the masonry external surface and coupled with a thermal insulation coating. The retrofit frames are connected to the masonry by means of epoxy anchors and to each other by means of steel rods. This solution has been proposed and conceived by the Italian company Progetto Sisma, who founded an extensive experimental and numerical campaign aimed at studying the effectiveness of this solution on the in-plane behavior of masonry piers. Here you can see a summary of the performed experimental testing, which consisted in a series of in-plane quasi-static tests performed on masonry piers belonging to two different masonry typology and typical of Italian construction and not yet extensively studied in literature. The first one was made of solid clay bricks in an header bond pattern, while the second one was made of hollow doppio uni clay bricks assembled in a Flemish bond pattern. The specimens were then tested in bare conditions. Then they were rebuilt and tested again in retrofitted configuration as shown in this slide. Moving to some experimental results, similarly to the previous retrofit solution, also in this case, the retrofit was not able to modify the pier initial stiffness and the initial failure mechanism, which was diagonal shear for all the tested prototype. However, the retrofit started to work only after masonry cracking, actually countering the relative opening of this diagonal shear crack, and therefore enhancing the pier displacement capacities. Indeed, in terms of displacement capacity enhancement, a factor of 3.9 was found for the header bond masonry, while a lower factor of 1.5 was obtained for the other masonry typology, for which a small strength increase can also be observed. Then, starting from this experimental data and with the aim of performing an extensive parametric study, advanced numerical models based on the distinct element method were built using the commercial software 3DEC. And according to this modeling strategy, the masonry elements are represented as an assembly of brick-shaped blocks, with the units that are expanded up to the thickness of mortar joints, and then contacts are generated between adjacent blocks. Then the behavior of these contacts or interfaces is described by zero-thickness contact spring, defined in both the normal and shear direction. As you can see here, constitutive models, user-defined constitutive models, were assigned to both the contacts and to the blocks to account for the complex and nonlinear tensile, shear, and compressive behavior of a masonry element. Regarding instead the modeling of the retrofit solution, it was modeled by as an assembly of finite element beams that were connected to the masonry by means of nonlinear deformable links available in the 3DEC environment. And as you can see on your right, the first displacement rule assigned to these anchors was actually calibrated based on dedicated experimental characterization tests that were performed during the experimental campaign. Here I'm presenting the numerical results obtained for the first masonry typology, and I want to point out that although we performed also the entire simulation of the cyclic test, and maybe we can discuss about this later, today I will only present results relating on monotonic loading. Because since the aim of the work was to perform an extensive parametric study, this study was not compatible with the computational time required by the simulation of the entire cyclic response of a huge set of masonry pairs. However, you can see that the numerical strategy adequately reproduced the experimental response, although you can notice an underestimation in terms of maximum strength. But looking at the ultimate displacement capacity, you can notice how the use of a monotonic loading pattern led to significantly higher displacement if compared to the experimental ones. However, looking at the benefit of the retrofit solution that is represented and compare in the red box on your right, you can see how, even using a monotonic loading, the benefit of the retrofit was closely captured, therefore enabling the use of this model for a parametric study. Here you can appreciate the results for the other masonry typology, where actually similar considerations can be carried out. Moving then to the parametric study, besides the two considered masonry typologies, two additional variables were considered. The first one was the pier length, and the second one was the level of overburden stress. In particular, 4 different lengths were considered, depending on the number of retrofit modules installed, while 3 different levels of overburden stress were accounted for, simulating, let's say, a lower bound, an upper bound, and a middle value of typical value to which masonry members are subjected in real case buildings. Regarding instead the monitored quantities during each of the 48 performed pushover analysis, they can be divided into 2 main groups. The first group is the simplest one, let's say, with the maximum base shear, the associated drift ratio, the failure mode, and the ultimate drift ratio. Instead, the second group of parameters, they consisted in the maximum relative displacement of the joints and in the maximum tensile or shear strain of the finite difference blocks. The idea of controlling this parameter was to compare this set of parameters at the same level of drift ratio to quantify how much the retrofit was able to reduce the damage in the meso-relief. Here you can see a summary of the results obtained for the head-and-bone masonry. And you can see that overall the retrofit reveals a good performance, not a lot in terms of increasing the maximum strength as expected, but in enhancing the pier ultimate displacement capacity. And although you can see that no clear correlation can be found between the retrofit benefit and the overburden stress, you can see how the benefit of the retrofit solution in terms of ultimate displacement capacity decreased with the increasing of pier length. And similar results were also obtained with the other masonry typology. Results are summarized here. Then, shortly introducing the complete assessment of the retrofit performance benefits, it was assessed by defining, starting from the quantities that I introduced before, we defined 6 different ratios that aim actually at quantifying the retrofit performance by a value of this ratio higher than 1. So actually doing the ratio between the retrofitted quantities and the reinforced one, or vice versa, aiming to quantify the retrofit, the positive retrofit benefit with a value higher than 1. Here you can see the obtained results related to this 6 ratio in terms of radial plots for the first 2 pier lengths. And overall, you can see how the retrofit was not able to modify the pier lateral strength, but allowed a significant improvement in both terms of damage mitigation, but also in terms of improvement of the displacement capacities. And for these 2 pier aspect ratios, average values of 3 and of 1.9 in terms of increasing the ultimate displacement capacity were found. Moving then to the longer pier, you can see how the retrofit benefits here are drastically reduced. So not only in terms of enhancing the pier displacement capacities, for which lower values of 1.5 and 1.3 were observed averagely, but also in terms of reducing the damage. And actually these results are fundamental because suggest that the retrofit benefits should not be assessed in an absolute way, but should be defined considering their dependency with the properties and the behavior of the meso-relief. Actually, the decreasing performance of the retrofit solution with the increasing of pier lengths can be explained looking at these numerical crack patterns. In red, you can see the relative displacement of the joints, so actually the cracks in the mortar joints, while in blue, you can see the damage in the blocks. And here we are looking at a comparison between the crack patterns of unreinforced and retrofitted walls at the ultimate condition of unreinforced piers. And can you appreciate, actually for the first two pier lengths, the retrofit was significantly able to countering the opening of the relative shear cracks, while this was not noticed for the longer pier. More importantly, looking at the ultimate condition of the retrofitted pier, you can notice how for the first two pier length, the retrofit was not able only encountering the relative opening of the diagonal cracks, but also enforcing a flexural response of the piers. That can actually explain the much higher displacement capacity that was observed for these two pier lengths. While this, of course, this mechanism was not noticed in the longer pier that is presented on your right. Here you can see the publications related to this second retrofit solution, and then we can move to the conclusive section. Overall, my research revealed a good seismic performance of both the studied retrofit solutions that are based on retrofit frames applied to the masonry. And both the solution allowed a good enhancement of the pier in plane response and allow also an enhancement of the building structural integrity, as clearly denoted by the full-scale shake table test. Moreover, the retrofit were not able to modify the pier or building initial stiffnesses because of its reduced stiffness if compared to the masonry, and also to delay the onset of damage. Moreover, we found that the effectiveness of the solution was found to be dependent not only on retrofit details, as expected, but also on the behavior of the masonry leaf. Therefore, looking at the field of innovative retrofit solutions, so actually not directly conceived for structural purposes, but maybe looking at energy efficiency requirement and cost effectiveness and lightweight before, in this field, reliable advances can be made only by coordinating dedicated experimental testing with the development of reliable models able to extend experimental results, enabling a comprehensive view on the retrofit benefits. Moreover, the results that collecting the results coming from both numerical and experimental evidences is then possible to develop in a relatively short time some design guidelines that can assist engineers in real practical applications. Moving then to some topics for future research. The first one is that the applicability, the structural efficiency, and the limitation of the investigated retrofit should be addressed in detail, considering the variability that existing masonry can exhibit. So not only related to the mechanical properties or to the typology, but also related to the quality. Indeed, considering, for example, a stone masonry, composed by irregular stone blocks with poor mortar, is a masonry that has a tendency to lose integrity. And therefore, the efficiency of this retrofit solution has to be studied more in details. Moreover, in literature, there is still a lack of available data on the experimental performance of retrofitted masonry piers, retrofitted, I mean, with this retrofit solution. And although the effectiveness of this solution, let's say, that is well recognized on preventing the out-of-plane failures of walls, further data would be necessary for the development of advanced model to account for both the in-plane behavior, the out-of-plane one, and maybe on their mutual interaction. Moreover, concerning the steel-based retrofit solution, as maybe you noticed, the study layout of the retrofit did not include the connection between the frames and the adjacent floors. However, in real application of this retrofit solution to an entire masonry facade, these connections are provided. So therefore, the retrofit effectiveness should be assessed also considering the result and maybe a simulation of the realistic scenario of a masonry. And concluding, the studied retrofit solutions were conceived in the framework of integrated retrofit solution. Therefore, energy efficiency aspects should be combined with the structural ones that I discussed today to investigate the optimal selection of retrofit details. So not only from the improvement of the seismic performance, but also in terms of sustainability and life cycle thinking. I can conclude saying that experimental testing and numerical analysis are two fundamental techniques that are both fundamental for the study of physical problems so complicated as the one that I presented today. Thank you for your attention.
Thank you, Nicola. So we'll start now with the questions from the committee with Ivan.
Thank you. First of all, I want to congratulate you on the good presentation on a very interesting research in what is a topic that is gaining more and more attention, both from industry and academia. So I have some question or more curiosity that I want to ask you. The first one is general, and I might be a little biased in what I'm going to say, but from what you have shown us, it seems that in the two retrofit techniques that you have studied, the timber-based seems to provide more benefits because you also have an increase in capacity, while with the steel-based, especially slide 33, the ratio was 1, so there was no gain. So the question here is, have you studied and investigated what would be the effect of the timber-based retrofit on, let's say, thicker walls, where maybe it might be diluted a bit, especially in terms of capacity increase, and on the other side of the steel-based retrofit, what would be the next step to improve the capacity? Because there's a little bit of material cost and labor costs, and which also it's on the favor of the timber-based, but I suspect that maybe by replacing the diagonals in the steel-based, you'll have a better response, and also looking into the connection.
Okay, thank you for the interesting question. And so I can say that basically the two retrofit solutions were actually, let's say, different, because the first one was a multi-component that were conceived aiming to design each of the retrofit components involved in the in-plane response. So actually, let's say that the strength increase can be controlled by, for example, selecting different connections or maybe different cross-section of the materials. While looking at the other retrofit solution, it was directly proposed by the company. So actually, the, let's say, that they present is, let's say, fixed. So the performance cannot be enhanced. Of course, I have to say that from the preliminary analysis that I'm carrying out about the connection of this retrofit with the floors, of course, an higher strength benefit was found. Of course, not a lot, but we are talking about the 20% or something like this. But let's say that for the steel-based retrofit solution, the timber cross-section are fixed. The same company is at the moment studying alternative retrofit solution, so trying to maximize the siding performance, or actually between the siding performance, and the cost effectiveness. But I think that let's say that in this case, we cannot a lot play with the different retrofit components. While looking at the timber retrofit system, that was, as I told before, as a multi-component one, of course, different solution can be, let's say, conceived. For example, thinking to apply the retrofit to thicker walls. Maybe in this case, a better solution should be the direct application of the OSB panel directly to the masonry. So not relying on the timber frames, because
maybe thicker a bit also.
What? Sorry?
And also a little bit thicker.
Yeah, exactly. Because in this case, of course, we try to minimize the invasiveness of the retrofit. That actually the thickness of the retrofit was the timber post plus the USB. So we try to reduce at maximum the thickness of both the components, while applying directly a timber panel that maybe should not be a OSB, but maybe a cross-laminated timber panel with higher strength and stiffness, can maybe have a positive performance of thicker and longer walls.
Thank you. And well, I have a couple more, maybe a little bit more specific questions. And the first one is, my understanding is that the design procedure that you developed, it's based on a capacity design, which is very good. And I would like to ask you if you could tell us a little bit more about the rationale behind, for example, selecting the C1 connection for being the fuse rather than C3, which...
Okay, yes, I think that we selected the C1 because for the problem that we studied, all the piers were very slender. So actually the flexural response was the predominant one, or at least was easy to induce a flexural response by preventing the diagonal shear failure. So actually we designed the retrofit in this, let's say in this view. So actually controlling the force, the maximum lateral strength with the C1 connection. While indeed, I can say that the formulation that were prepared before the experimental testing actually relied only these simple mechanics that is actually like, for example, reinforced masonry. That is actually pretty similar. So actually we started, like, let's say, in analogy with reinforced masonry, so to provide a contribution to the flexural strength provided by the timber posts and their connection that are like vertical bars, and the USB sheeting like the horizontal ones, let's say.
So maybe next step you might be considered to have C1 connection that are stronger than C3, so you can exploit all of their capacity.
Yes.
Okay. And the other question that I had was about the modeling that you showed. So my understanding is that the assumption is that the two systems, so the masonry and the retrofit system, are responding in parallel, and which is a strong assumption, which might be correct, but means that you are neglecting the C3 deformability.
Yes,
and
of course.
So you have, the first question is, in the model you have a rigid connection between the nonlinear truss that simulate the timber posts and the two nodes macro element for the masonry? And if yes, what's the role of the C3 connection?
Yes, so actually yes, in this simplified modeling that we employ nonlinear macro elements, of course, there is a rigid connection between the nodes that I'm presenting here from 1 to 7 with an offset that were connected with rigid links, of course. So actually we are neglecting the deformability of C3 connections, but looking at actually the damage that was observed here in the in-plane test, actually the connection were not actually damaged. So we deemed that was a reasonable assumption to consider this rigid connection. Of course, if I had the possibility to use a different modeling tool, such as, for example, a distinct element method, of course, in this case, the deformability of the connection should be accounted for.
Okay, so last thing, the follow-up question based on your reply. So if there wasn't much damage or deformability in the connection, then I've seen that you've considered some overstrength, so confinement effect due to the connection, which kind of relies on engagement of the connection, so how does that relate with this?
Okay, this actually was one of the most complicated topics in the definition of the analytical formulation that maybe I reported at the end of the presentation. Wait. Yes. Okay, so actually, from both experimental, especially from numerical evidences, we actually we found that by adding the retrofit frame only without the USB sheeting, so only providing a flexural contribution, so actually the entire flexural strength that was captured corrected by the model because of the simple mechanism could not be reached because the masonry failed in shear before. So that actually suggested that there is a kind of, let's say, confinement effect provided by the retrofit solution that countered the opening of this diagonal shear in the initial phase of the test. I mean, a very short drift ratios, so allowing the pier to exhibit a flexural response. And so actually, we try to account for this confinement effect by considering that actually the C3 connection between, along a diagonal, a hypothetical diagonal shear cracks can, let's say, contain and avoid the opening of this for very small displacement. And of course, I know that considering the full strength of this connection for the contribution is, of course, a strong assumption, but at least for both the, let's say, for the full-scale piers and for the buildings, it worked in terms of prediction of the analytical results. Of course, this formulation have to be proved with other, let's say, experimental tests available on this retrofit topology.
Okay, thank you very much for your replies, and congratulations again.
Thank you.
Quickly, first of all, thank you very much for the presentations, very nice. Just some questions. The first one, for the timber structure, you told to my colleague that you used a capacity design approach also for connections and so on. What happens if when measuring damaging increases, in the sense you can have some change in the capacity design because of damaging?
Of course, actually, the capacity design procedure was developed favoring a flexural response, of course.
Okay.
And then all the design of the other components were done in capacity design, starting from the flexural strength of the pier. I'm not sure to have some slide today, I don't think so. But so actually the first step is represented by the definition of the target performance improved provided retrofit solution that should be okay here. So actually by designing the strength contribution in terms of flexural contribution, then actually the dimension of the panels has to be selected aiming to provide a flexural mechanism of the pier. Of course, if it is possible, depending on the pier aspect ratio.
Yeah, okay, but if the interaction between your system and the masonry can change during the earthquake because of damaging.
Yes, of course, of course.
So you have to take into account it because the distribution of deformation and of internal forces can change during the earthquake. For example, if a crack interests some part of the connection of your system, it means that that connection can have a different stiffness and different capacity.
Yes, of course, I agree with that. But actually applying, because the procedure that we designed, the capacity design procedure, was applied to the pier that we tested in plane. So actually we designed all the components to provide a flexural strength contribution. Yeah, okay. I know that is not so easy, but our idea was just to promote the failure associated with much higher displacement capacity rather than the shear one.
Okay, the second question is, what if you analyzed the really homogeneous masonry pattern and homogeneous systems, no? What happens if the behavior of your masonry change locally because of the
You mean with an irregular masonry, for example?
Exactly.
Yeah, of course. With this.
Often you have in the reality non-regular masonry, no?
Yes, yes. Of course, I think that, further study that needed to study the applicability of this retrofit to this kind of masonry, of course.
That's okay. No,
but I think that in these cases,
it's a question for the future.
Yes, of course. We can maybe change how the connections between the retrofit and the masonry are done. For example, in these cases, we were using only chemical anchors, but maybe for thicker walls, made, for example, of stone, we can think to do some passing, let's say, connectors to first provide a global behavior of the pier, so to avoid the loss of integrity, let's say. And regarding this topic, we are actually testing a further version of the steel-based retrofit system that is also applied to stone masonry, and so a kind of this system has to be tested in the following months.
Last question is if the pattern of reinforcement are like you showed in that plan.
Sorry, in the pattern?
In the pattern of the reinforcement, it interests also the internal walls, as you showed on the conine. No, the pink. No, you. Oh. This is the plan of your. Ah, no, it's the. Okay, no, it's the wall. If you show the photo, you see
okay,
that
maybe, yes, maybe
you reinforce it more both external and internal walls.
This one. Sorry, this photo is from. Here I have a photo that is a better resolution. That should be here, I guess. Okay. So these are actually the timber shear walls that are commonly employed in the United States. Okay. So actually the idea of applying the OSB to the timber frames came directly from the American prescription for this technology.
No, I didn't understand. But if you reinforce internal walls, it means that you have to change also foundation. It's not easy.
Yes. So
for external walls, I mean that it's easier in some way, no? But for internal, it's not so often so easy, no?
Yes, but by doing an intervention from the external point of view, you cannot preserve the external facade, let's say. So it depends.
You cannot preserve the facade, but it's easier then to absorb shear force or increase of shear force due to the increased behavior of your structure.
Yes, I agree with that.
but that's just for discussion. Thank you very much.
So first of all, congratulations for your presentation, for your work. And I had just a couple of curiosities. First of all, about cost. I don't know if you have an idea, since you presented two different retrofit solutions, and we also have an idea of the seismic performance. I don't know if you had a look also at costs of these two retrofit solutions, and so if you can provide some further details about this aspect.
Okay, so I start directly from the steel retrofit solution. About this retrofit, we don't have a lot of information because the retrofit came directly from the company, so for them was already the optimal solution. While looking at the timber-based retrofit solution, because of the multi-component nature, so we can check the price of all the components involved, we found that actually the cost was very similar to other retrofit solutions that provide a similar reduction in terms of vulnerability, like for example CRM or FRCM.
Okay, thank you. And then I'd like to know if you have an idea of the applicability of this kind of solutions, timber-based or steel-based, both of them. For example, for measuring fields in reinforced concrete frames. So I think it can be somehow similar. And so do you have an idea about this kind of application?
Yes, of course, they can be also applied for the retrofit of measuring infills. Of course, in this case, Professor Jongo is studying something very similar. So actually, there are two different possibilities. So, or applying to the external surface of the building, so actually connecting the different nodes of the reinforced concrete frame, or even by replacing the infill by actually directly a CLT panel or a OSB1. So actually, the solution can be different, but it works, and there are a lot of experimentation and works that will be done on this way.
Perfect. Last question. I saw some monotonic response that you obtained in the more refined modeling analysis that you performed for steel retrofit for this one. Did you try also to reproduce this strategy?
Yes, I can show you the results that I don't have a lot of time, so I reported the slides here. Okay, so here there is the cyclic response simulated with the distinct element method for both the masonry typologies. And you can notice that in the first case, for the Edermont masonry, the degradation was very close to the experimental one, although there was always this kind of small underestimation in terms of strength. And also the shape of the hysteresis cycles was very close to the experimental ones. While moving to the other masonry typologies, although the pushover curves that I presented before was very close to the backbones of the results, looking at the simulation of the cyclic test, you can notice how the degradation was much higher, and also the shape of the cycle was not perfect. But because of the mechanism that the software predicted, that was not exactly the same, I mean, looking at the cyclic test rather than the monotonic loading one.
Okay. And obviously this kind of modeling strategy can be applied also to the other retrofit solution.
Yes, of course.
Similarly. Okay.
But actually, yes, actually I had the possibility to start to work with them only after the first campaign was ended, so I not a lot of time to, let's say, integrate this modeling solution with the last one.
Okay, thank you.
Thank you. So we have exhausted, actually we went beyond the time allocated for this discussion, so I will not be opening the questions to the public. Thank you once again, Nicola. And the next candidate is Gianrocco Mucedero. We will keep seeing work related to masonry infills in this case, because Gianrocco is going to present us his research on large-scale seismic risk assessment of existing masonry infilled reinforced concrete buildings in Italy. Gianrocco.
Thank you, Professor Montero, for the introduction, and thank you all for attending this presentation. So the work that I'm going to present is focused on large-scale seismic risk assessment of existing masonry infill buildings, And in particular, it was conducted under the supervision of Professor Montero and Dr. Daniele Perrone. So I would like to start this presentation talking about the losses in Italy. Why? Because they are quite impressive. 5,000 people died, 500,000 people lost their own home for a cost of 150 billion of euro. Conversely, the total amount in seismic prevention is close to 1 billion of euro. So nowadays, the level of awareness about seismic safety is increased, and so now we have guidelines for seismic risk classification and also tax deduction that are a unique opportunity to improve our building portfolio. So if we took an example of the 2009 L'Aquila earthquake, we can notice that 90% of the costs are related to non-structural element, in particular damage to non-structural element. 47% infill wall and partition, 16% plumbing and electrical systems, 22% windows and doors, 50% other elements. In particular, plumbing and electrical systems and windows and doors are generally incorporated in masonry infill and partition. So it's quite clear that masonry infill have a strong impact on both global and global behavior, but at the same time leading to high economic losses. And given that, and trying to fill a gap between the engineering practice and the research field, we focus on four different main aspects. The variability of the masonry infill in terms of material properties and their modeling approach, the impact of the masonry infill variability on the structural performance of existing buildings. Then we move to the risk assessment, because generally we consider aleatory and epistemic uncertainty. So the idea was to better quantify the impact of the masonry infill variability when we account for the epistemic uncertainty. And finally, the impact of the masonry infill variability on flow response spectra, on the seismic demand on structural elements. So all of these main aspects were addressed in 4 different chapters, which are strictly connected to each other, because the main outcomes and conclusion of each chapter is the starting point for the next one. So let's start with chapter 2. If we look at the collected database of experimental tests, it's quite simple to notice that there is a huge variability in the mechanical properties of the masonry. And since there are no in situ tests to characterize the masonry infill typology, it's quite difficult to guess the specific material properties in a specific building, in existing building. So the idea was to propose a macro-level classification of masonry infill according to their stiffness and strength that is able to cover the wide range of variability that we notice in existing database. And in particular, since the variability is not only related to the material and geometrical properties, but also the modeling approach that we use, we decide to collect the most used equation in literature, for example, for the definition of the strut width, for the reduction in case of openings, and the strength models and the backbone curve. So by combining all of these parameters, the idea was to find the best modeling approach for each masonry infill typology. In particular, we used this modeling approach in which most of the backbone curve were proposed by O'Reilly and Sullivan in 2017. We further validate the numerical model using experimental tests, in particular gravity and seismic load design frame. And the model is quite able to reproduce the experimental test. And once the numerical model was able to validate to be close to the experimental results in terms of bare frame structural configuration, we moved to the infield frame. So due to time constraint, I'm not going to the detail of each modeling validation for each masonry infill, but I will show you the numerical modeling validation using the experimental test of Morandi et al. In 2018. In particular, given a specific masonry infill typologies and given, let's say, the backbone curve proposed by Bertoldi, we can change the strength model and the strut width, and in particular, we got all of these backbone curve. By using all of these backbone curves, we can run pushover analysis, and we got all of these pushover curves. So you can notice that there is a huge variability with respect to the experimental test. We are talking about 500 kilonewton of differences by changing the numerical model. So at the end, using statistical parameters and, let's say, the mean, the standard deviation, we were able to find the best numerical model for each specific masonry infill typology. If we look at the disaggregation of the results, the strut width has no impact on the results, whereas the changing is due to the changes of the strength model. So the most important parameter is the strength model and not the strut width. So at the end of chapter 2, we can say that the macro level classification is able to cover the wide range of variability. The strength model, the backbone curve are the most important parameters, and the selection of a priori model to characterize the hysteretic behavior of mesoid infill should be completely avoided. Why? Because generally in seismic risk assessment studies, an a priori selection of mesoid infill typologies was used to characterize the mesoid infill variability. So the idea here was to propose a macro level classification, to validate it, and then to apply to a large building portfolio. And to do so, we develop a fully integrated building stock, where the main parameters are here, and in particular we focus on reinforced concrete frame and on residential buildings. In terms of construction age, we focus on the 70s because the massive portion of our building portfolio were built in that specific period, in which most of the Italian regions were not classified as seismic prone. So this is some information related to the building portfolio. In particular, the building portfolio consists of 108 geometrical configuration. We consider 5 different structural configurations: bare frame and fill frame with and without openings, and pilotis again with and without openings. We consider the 5 different mesoid infill typologies, as I said, classified from weak to strong, and we design all the frame using the simulated design approach. At the end, the number of buildings are close to 2,000. So we use this research methodology, and in particular, the idea was to characterize through a pushover analysis the building portfolio. And the results were disaggregated with the idea to quantify the building to building and infill to infill variability, but then all the results were aggregated with a view to regional-oriented seismic risk assessment studies, in which maybe we can have the necessity to have specific characteristic points of the pushover curves. In particular, looking at the building-to-building variability, this is quite important in case of bare frame. In particular, the variability with respect to the maximum seismic coefficient is in the order of 13 to 16% and increased to 30% in case of 4 or more story buildings, due also to the aggregation of different building aids, whereas in case of infilled frame, this variability is in the order of 4 to 5%, and increased to 60% for 4 or more story buildings. If we look at the intra-building variability, so infill to infill variability, by changing the geometrical configuration, the results are practically the same. Whereas looking at the variation of the pushover curves given by a different mesoid infill, there is a huge scatter in terms of seismic coefficient. If we now use all the mean and the standard deviation in just one plot, we can notice that the geometrical configuration has no impact on the results, whereas most of the variability is coming from each mesoid infill typology. Then, as I said, with a view to regional-oriented studies, we decided to multi-characterize the pushover curves, and we used the approach proposed by Dolcek and Pfeiffer, and we applied this approach to infill frame with and without openings and pilotis with and without openings, with the idea to propose a set of characteristic points that can be used for large-scale risk assessment, and the user can select a specific number of story, the typology of mesoid infill, if weak, medium, or strong, and a set of characteristic points with their dispersion, and to run a simplified tool like SPO2IDA or SPO2 frag, but accounting for building-to-building variability and infill-to-infill variability. Then we replaced the pushover analysis with the nonlinear time history analysis. We performed more than 200,000 nonlinear time history analysis with the idea to better characterize the structural response and the loss assessment, considering the mesoid infill variability. The numerical model was the same. I'm just going to present to you the results for 2 different intensity levels, in particular the damage limitation and life safety limit states, and we consider the collapse when as a function of the maximum interstory drift, or when the first member reached the collapse in shear according to the Italian code. So, looking at the interstory drift, in all of this plot, the gray area represents the building-to-building and record-to-record variability. As expected, introducing the mesoid infill in the building leads to a reduction of the interstory drift with respect to the bare frame, and in particular, this reduction is a function of the mesoid infill typology. If we look at this plot, we can say that having the mesoid infill in the building is beneficial for drift-sensitive non-structural components. If we now look at the peak floor acceleration, the trend is reversed. So introducing the mesory infill, we have high peak floor acceleration with respect to the base frame. So no more beneficial for acceleration-sensitive non-structural components. In terms of fragility curves at the building portfolio, we notice that buildings arranged with weak mesory infill, so the fragility curves that are the one in green in this plot are quite close to the bare frame structural configuration. So they are not able to produce any shear failure in their buildings, whereas all the other are shifted on the left, which means higher probability of collapse given at the same level, at the same intensity level. Then we use all of these results to perform a loss assessment at the building portfolio level, and we notice that increasing the stiffness and the strength of the masonry from type 1 to type 5, we are increasing the stiffness and the strength. Also, the expected annual losses increases, with the exception of one-story building, which we have the expected annual losses are quite close to each other, regardless the masonry infill typology. A clear representation can be obtained by this plot in which we aggregate all the results in terms of masonry infill as a function of the number of the story. Why it's important? Because in large-scale application for low-rise building, we can neglect the effect of the masonry infill variability in terms of impact on the expected annual losses. Such variability increases became more relevant when we go from 3 to higher story, 3 to more story buildings. If we aggregate the results in terms of geometrical configuration, increasing the stiffness and the strength of the masonry, also the mean of the expected annual losses increases. A clear representation is also given by this plot in which we have a surface of the expected annual losses as a function of the masonry infill and the number of the story. We look also at the coefficient of variation of the expected annual losses by aggregating all the masonry infill typologies per building 8. Why? Because in a large-scale risk application, maybe we don't know exactly the material properties of the masonry. We can have an estimation of the variability of the expected annual losses due to the masonry infill variability. We also propose a four-ordered polynomial that in a simplified way, the user can estimate the expected annual losses as a function of the masonry infill typologies and the number of the stories. So at this point, we already noticed that the masonry infill have a strong impact on the structural response, also in terms of collapse and loss assessment. And if we look at simplified procedure for the estimation of the expected annual losses that are foreseen in guidelines, let's look at the case of Sysma bonus, they are not able to account for different non-structural elements along the building 8 or in two horizontal direction, and also in case of torsional building with torsional behavior. So for this reason, we propose generalized story loss function that can serve as a valid alternative to the Sysma bonus procedure, keeping a low computational effort, and the results are quite accurate. In particular, we use the DEI, which is the Italian bulletin price of building typologies. We selected 15 building typologies characterized by a different building value. Each of these buildings is characterized by different structural and non-structural components that were classified in different component categories, and we used the repair cost incurred for the 2009 L'Aquila earthquake. So at the end, using the story loss function toolbox proposed by Sharanasian in 2021, we were able to obtain the generalized story loss function. Going into the detail in particular, this table represents an example of a building D in which for each component category we have different component groups, and for each component group we have a total cost, a percentage cost, which means an incident cost with respect to the construction cost, and finally a normalized cost, which means euro per square meter. We look at the cost of the construction cost as a function of each structural and non-structural component and component categories, and we were able to define 3 different building values, low, medium, and high. You can see here their related construction cost, and for the medium building value, the results that we got are close to the total grant that was found by the Italian government for the demolition and reconstruction after the 2009 L'Aquila earthquake. Finally, we used the repair cost proposed by Del Vecchio et al. In 2020, in which the repair cost is expressed as a function of different damage states and for structural and non-structural components, and we were able to propose generalized story loss function. I would like to say that for infill and partition, we condition the damage, so the repair cost, to both DDP, interstory drift and peak floor acceleration, because they are sensitive to both DDPs. And for plumbing and electrical system, we also have done the same, but this because their sensitivity to damage depends on their location, if they are in the mesory infill or partition, or if they are in the suspending ceilings. So at the end, with the idea to provide a more useful tool, we combine the building portfolio features and the story loss function, and we propose normalized story loss function, which are repair cost normalized with respect to the replacement cost. And why I say the more useful tool? Because the engineers or decision makers that would like to apply for tax deduction have to define the construction cost for architectural, structural, and building system. In doing this, they have to identify the most suitable buildings among those reported in the day, which is the same building catalog that we use to propose this story loss function. So once the engineer has selected a specific ID, can have access to the specific story loss function for his building. Finally, we also use the story loss function at the building portfolio level, considering and neglecting the out-of-plane failure of the masonry, and we notice that accounting, although in a simplified manner, the out-of-plane failure of the masonry, the median increment in terms of the expected annual losses is in the order of 3 to 19% as a function of the building value. So at the end of chapter 4, we can say that the infill-to-infill variability is quite important, higher with respect to the building-to-building variability, and should be accounted in future large-scale application. The effect of the mesory infill on the non-structural element depends on the type of the non-structural element, if they are sensitive to drift or acceleration. A reasonable estimation of the expected annual losses cannot be obtained neglecting the mesory infill variability. We propose a coefficient of variation of 40% for all of the cases in which we would like to have an estimation of the variability of the expected annual losses due to the mesory infill properties. And finally, the function that we propose can serve as a valid alternative to the Sisma bonus procedure. Given that, we can say also that for a large risk scale assessment and in risk assessment in general, we generally use epistemic and aleatory uncertainty. So we decide to quantify through a more refined approach the epistemic uncertainty due to the mesory infill variability and the RC shear failure in the building. Why? Because there are current gaps in literature. In particular, there is a little attention was paid to the variability of the mesory infill properties. The numerical model was generally selected a priori. A single strut modeling technique was used, which means to neglect the possible shear failure of the RC member due to the interaction between the mesory infill and the surrounding frame. And finally, the shear behavior parameters were generally not treated as a random variable. So we overcome these problems considering the 5 mesory infill variability that we prove to cover the wide range of variability of the mesory infill properties. For each of these, we use a specifically calibrated numerical model that was checked using the experimental test. 6-strut modeling technique was used, which means to account for the local interaction between the surrounding frame and the mesory infill. And finally, the shear parameters were treated as a random variable. So the idea is to quantify in a more refined manner the modeling uncertainty and to define their impact on the structural response in terms of collapse assessment, demand parameters, and expected annual losses. This is a subset of random variables that we consider. The model realization were obtained using the correlation reduced linear per cube sampling. And finally, the idea was to look at 4 different fragility curves in terms of record-to-record variability, modeling uncertainty only, total one, which means accounting for both epistemic and aleatory uncertainty, and considering all the records and all the model realization, and finally an adjust collapse fragility curves, by which, starting from a fragility curves in terms of record-to-record variability only, we can directly go to an estimation of both epistemic and aleatory uncertainty. In this slide, you can see that all the gray fragility curves are related to each model realization. The mean of these, which means the mean fragility curves considering only the modeling uncertainty, and a continuous black line, which is the record-to-record variability only. From this plot, you can see that accounting for the modeling uncertainty, we notice a shift on the left of the median intensity of collapse with respect to the record-to-record variability. The same also in case we consider the total uncertainty, and so we propose a reduction factor and a new beta to account for modeling uncertainty. Then we look at the dispersion of the engineering demand parameters. Why? Because generally in component-based loss assessment, we used the dispersion of the DPs to generate the realization. So we look at this problem. We also consider two different scenarios, critical stories and all stories. Critical stories means that the building has a soft story mechanism, all stories has a global behavior. And finally, we propose two sets of epistemic uncertainty for both test-story drift and peak floor acceleration as a function of the scenario. We use the more refined modeling uncertainty to propose new fragility and vulnerability curves that can be used in large-scale risk application for these specific building typologies, accounting for both infill-to-infill variability and building-to-building variability. Finally, the idea was to understand if the more refined epistemic set can have a strong impact on the expected annual losses, and to do that, we decided to compare the proposed modeling uncertainty set, which account for both measuring infill variability and premature shear failure of the RC member, with a modeling uncertainty that was proposed in literature, neglecting for the possible shear failure. We perform a loss assessment impact, so a component-based loss assessment. We use a case study building of a school, a real case study building in Italy. And I'm not going into the detail, I just want to show you that the more refined epistemic set leads to higher expected annual losses with respect to the modeling uncertainty that was proposed in literature. And this increment is in the order of 28% in case of infill frame without openings and 33% in case of openings. So at the end of chapter 4, we can say that the modeling uncertainty has a strong impact on the results, especially on the reduction of the median intensity of collapse. We propose an epistemic set, and we propose a reduction factor and epistemic uncertainty for the median intensity of collapse. We also propose two different dispersion of the engineering demand parameters as a function of the scenarios and for both interstory drift and peak floor acceleration. And we look at the impact of this more refined epistemic dispersion set on the expected annual losses. And we notice that the more refined one are 1.3 to 1.8 times higher with respect to the one that was proposed in literature. And in particular, starting from the disaggregation of the expected annual losses for the school building, we notice that increasing the stiffness of the masonry, we are also increasing the damage to acceleration-sensitive non-structural components. So given that, we decided to go into the detail and to look at the impact of the masonry infill variability on the flow and response spectra and on the seismic demand on structural elements. In particular, this is the research framework. Again, we use nonlinear time history analysis. We derive the acceleration flow response spectra at both first and roof level. And finally, we look at the impact of the masonry infill variability on the seismic demand and on the generation of, derivation of the acceleration flow response spectra. I'm just going to show you the results for bare frame and uniform infill frame. And in particular, in this slide, you can see that there are the acceleration flow response spectra for bare frame and infill frame recorded at both first and roof level at life safety limit states. What we can say that the gray field area represents building to building and record to record variability, whereas in case of the infill frame, there is also the infill to infill variability. The shape of the acceleration flow response spectra is quite smoother for bare frame, whereas we notice a very well-defined peak in case of the infill frame. The spectral acceleration of the bare frame are quite lower with respect to the infill frame. And finally, if we look at the roof story level, for example, we can say that the variability in the size in the mesory infill typology leads to a strong impact on the spectral acceleration. We have a variation of the spectral acceleration in the order of 29 to 60%. Given that, we decided to go into the detail, and in particular to start to investigate each component, trying to propose a more refined approach to develop acceleration flow response spectra accounting for the mesory infill variability. In terms of component factor, we noticed that increasing the stiffness of the mesory, the component amplification factor at the first level decreases, whereas at the roof level increases. If we look at the variability in the seismic demand, in particular for flexible and rigid non-structural elements, for rigid non-structural elements, you can notice that increasing the mesory infill, the stiffness of the mesory infill, the seismic demand of the non-structural component, which is rigid, increases. Whereas for a flexible component, the trend is completely reversed, so increasing the stiffness of the mesory, the seismic demand on a flexible component decreases. So concluding, the impact of the mesory infill, or different mesory infill topologies on the spectral acceleration is quite relevant. The component amplification factor was noticed to have a different behavior as a function of the mesory infill typologies and the location of the non-structural elements. And the last one, more important, I think, for engineering practice, is that the seismic demand in the non-structural elements can be overestimated or underestimated up to 50% due to the mesory infill variability. So although a lot of work was done, there is always something to do and to improve, and the case study building portfolio can be extended to different periods of construction and design level with the idea to quantify the differences in terms of structural performance, loss assessment or collapse assessment. A more refined estimation of the expected annual losses at the building portfolio level can be obtained accounting for the out-of-plane failure of the mesory into the numerical model. The generalized story loss function can be proposed also for other type of buildings, let's say school, hospital, and so on. We are also working on environmental story loss function that ever been proposed, and they represent the expected environmental losses due to damages and the repair action after a seismic events. And finally, we are also working on the probabilistic estimation of flow response spectra to account for the mesory infill variability. So all of this work was based on different journal and conference paper, and I would like to thank you, Professor Montero and Dr. Daniele Perrone, for supporting me during these 4 years, and thank you all for attending this presentation.
Thank you, Gianrocco. 27 minutes. So let's start with the questions from the committee, starting with Teresa.
So thank you, and congratulations for your work based on very extensive numerical analysis, and congrats for the presentation. I have some comments, some remarks. First, a general comment that is about the fact that in all your analysis, obviously also to reduce the computational burden, you often use 2D frames to reproduce the response of a 3D building. And so I'd like to ask you if you think that this approximation is fully generalizable, when, and so what we can done to take into account also this issue.
Thank you for your question. Yes, all the models are 2D, and as you said, the problem was the computational analysis of these of the large building portfolio, because there are more than 2,000 buildings. So for sure there is a limitation in terms of maybe the expected losses can decrease or can increase. We don't know, but still, I personally think that to draw general conclusion or starting point to starting to think to the variability of the measure infill and their impact on large-scale building portfolio is a reasonable assumption. Given that, I think that 3D model should be done, should be considered, and in line with this, we are still working on it. We are trying to replicate all the 2D models in 3D and to restart all the computational analysis to draw general conclusion that can be very general conclusion.
Also including aspects, as you mentioned.
Yes. For this reason, I say that the next point is to include the measure infill, the out of plane, because otherwise it's quite difficult and there is less impact on the results.
Okay. Then I have just another question about the shift of the median capacity of fragility curves at collapse that you mentioned some slide before, about the considering the infill's variability or not, so in comparison with the record-to-record variability only. This shift, exactly, this shift is significant in terms of median capacity, for example, and I was wondering if you have how do you explain this kind of reduction in seismic capacity, basically?
Thanks for your question. If we look not at these results, but the building portfolio level, you can directly notice that accounting for when we start to consider a strong measure infill or medium to strong measure infill, we still have a strong reduction of the median intensity of collapse. So these results can be firstly conditioned to the 4 measure infill typologies that are maybe too stronger with respect to the surrounding frame, and given that we have this strong reduction. But at this point we have also a lot of variation in all the parameters, let's say the shear parameter, so stirrups, spacing and so on, the concrete and steel properties, and all the other properties that are changing. So this strong reduction is due to all of these changes in this parameter. And I think that could be reasonable to consider this type of reduction, because in general, also in terms of median intensity of collapse, it seems more realistic, the modeling uncertainty only with respect to the record-to-record variability, especially for gravity load design with for 3 or more story buildings.
And so I think, and you also mentioned that there is also a big influence of the local shear interaction.
Yes.
Okay, and so do you analyze, do you consider the strength parameter as random variables?
Yes.
Okay, and do you also try to, did you also try to use several different strength models with respect to the model that you mentioned, the SEDS and Emile?
Yes,
okay.
yes. No, we just used that one. We didn't change the strength model. So all let's say that we always use the numerical model that we were able to say that is able to reproduce the experimental test. So if in all the numerical modeling validation there was the model of season, we also used that one in the epistemic uncertainty work. So, but still can be a good point to change, let's say, the strength model using another one and trying to understand if there is a strong impact on the results.
Maybe its variability is already included within the variability of random variables that you consider. Okay. Just a final curiosity. So in light of your extensive analysis, I'd like to ask you if you think that since the great variability of measure infills, if decoupling infill from the RC frames can be or not a good solution of retrofit, let's say, for the reinforced concrete frames?
I personally think yes. I personally think yes, because there are 2 options. Or you start to improve the RC frame and then you apply, let's say, other type of intervention to prevent in-plane, out-of-plane failure. So prevent, let's say, to be sure that the frame is not going to collapse and also that there is no out-of-plane. Otherwise, I think that it's better to create a gap and to retrofit only in terms of out-of-plane failure.
Thank you and congratulations again.
Thank you.
Just a couple quick questions and general consideration. The consideration is that it's really general and it's for the future again. No, not you are really happy to be arrived at the end of your PhD, no, probably, and you wish to tell us all several thousands of numerical simulations you made during the last years. No? But I think this is just a suggestion for the future that the capacity of a researcher, but also of an engineer, to transmit what he did, it's really the bigger part of our work. And it means that when you organize a presentation, I think that you should show much less pictures, much less formula, much less numbers in one slides, probably less slides, concentrating yourself on the conceptual part of your work and not on the colored graphs and so on. What it's real enthusiastic for our work is the conceptual part, no? Because the engineers, idea, and the idea are really rare and precious. So my suggestion is to maintain your enthusiasm for the research, trying to be more effective in the presentation, okay, and more strict in the.
Let's say that with a lot of topic that we addressed and a lot of things that we have done.
Synthesis, it's really difficult to be reached. You are too young now, but when you will become older and older, like me.
Thank you for your suggestion.
Just a question. The filled frame of your simulation are all regular in the shape, so the same now.
You mean in plan?
In plan, yeah, exactly.
They are 2D buildings, and
but are regular. It means no.
In the span lengths.
In spans in the 8, all the floors are the same, or
the span
use of
ranges.
The floors are the same, so the shear for each.
No. The span length ranges from 3 to 5 meters.
But they are free for all spans.
They are?
For one frame, 3 meters for all spans.
No. They change. No. They change also in plan. Okay. So they are also, let's say, irregular.
So they are not regular frames.
Both.
Also. Both. Okay, just a question. And the second question is, I saw a really long list of render variables. It's this one. How did you find the information of all that random variables?
All these information are based on...
About the distribution, the mean value, the variance, and so on. It's really difficult, in my opinion. And all of them are really relevant in your calculation, in your evaluation of reliability of your system.
All of these random variables were based on literature review. So we check the literature and we try to find the best parameters. In terms of median and dispersion, most of these are based on the work of Hazelton. Yes, all of these parameters in general are quite important to be accounted for. But then, if they have no impact on the results, there are no, let's say, relevance, right?
Yeah, you're right. Just to understand how you organize your work. Okay, thank you very much.
Thank you. I had actually a couple of questions, but you partially already replied, so I already know the answer thanks to previous questions from the colleagues. So in terms of building-to-building variability, what actually did you account for? Because at the beginning I thought it was also the plan, but then you explained that it was not the case.
Thanks for your question. In terms of building-to-building variability, we changed the span length of the building. We consider the different building length and span length, and also different building heights. So the building-to-building variability, so geometrical configuration, is coming from these parameters.
But not infill layout?
No, the infill layout, no. Is the infill layout, let's say that we account in a different way. Infill frame, and we account for infill-to-infill variability and building-to-building variability. We account for the openings. Okay, we have run again the analysis, and the building-to-building variability is a different value. Okay. So for each of these.
And you mentioned when you refer to the strength model, you mean also the way it's the basic model, so if it's a single strut, eccentric strut, three struts, that, or it's just the behavior attributed to the three strut that you...
In the numerical modeling validation?
Yes.
In the numerical modeling validation, I refer to, let's say, the equation to define the strength capacity of the masonry. Let's say the one that was proposed by Bertoldi, or the one Panaggio, Taxo, and Fardis, and so on.
But in the validation phase, you also consider different modeling approaches?
Yes, we change all the modeling approaches, so all the strength, the backbone curves, all the strength models, all the equation for the strut width, and all the equation for the reduction in stiffness and strength.
But not the type of strut?
The type of strip was a three-strut modeling approach.
Okay.
Was already let's say at this moment the best modeling approach.
Okay, so you might have already explained that in the presentation, but I probably missed it. So in chapter 4, when you, I believe you analyzed the model variability, you adopted a single strut.
For the in chapter 4?
I think it was chapter 4, yes, you adopted.
Chapter 4 is epistemic uncertainty, and here there is a three-strut modeling approach.
Okay, so maybe not chapter 4, but at some point you used, is that correct?
I think for the loss assessment at the building portfolio level, we use a single strut modeling technique, but we account for shear failure through a post-processing technique. Using the approach of
So you added the additional shear?
No, we check at each step of the nonlinear thermistor analysis the maximum shear, the maximum axial forces in the strut, and then we decompose the forces, and we added the shear at the shear capacity, that level of shear, and trying to understand if there is a failure. Okay,
thank you. And last thing, the out-of-plane capacity, how did you exactly assess that?
For the epistemic, you mean for the loss assessment, right?
Yes.
In that case, it was just a simplified approach. We used the peak floor acceleration at the specific floor, and we used that value comparing to the median intensity of collapse of the fragility curves for the out-of-plane that was proposed in FEMA.
Okay.
It's not modeled.
So it was not directly assessed?
Yes, exactly.
Okay. Thank you.
Thank you.
Okay, so we haven't actually exceeded the 45-minute slot, but we are 10 minutes behind schedule, so I will now let everyone have a break. So the coffee break ends at 4:30 sharp, okay, so we need to start again here, remaining presentations. Thank you again, General.
Thank you.
also issues with your presentation?
I think no, I checked.
Very well. Let's move on now with the last two candidates. And the first one is already here with me, ready to present. So Volkan Ozarac. Volkan will be presenting his thesis on the integrated evaluation of earthquake-induced economic losses for multi-span reinforced concrete bridges. Volkan.
Sorry. Good afternoon, everyone, and thank you for joining here today. I will start my presentation with a cartoon summarizing briefly one of the main problems we have. Over time, if not maintained well, the structures tend to become more vulnerable to the hazards, with seismic hazard being no exception. Moreover, as we expand and build more structures in earthquake-prone areas, we put more structures at seismic risk, and thus overall seismic risk of national asset inventories keep increasing. Consequently, there is a growing need to develop seismic risk reduction policies, yet to achieve successful policies, risk-informed decision and sound understanding of seismic risk is required. This is only possible with a well-established methodology to assess the structures, such as performance-based earthquake engineering, and the deep understanding of each contributing factor we see here. In this sense, my focus here is on the seismic risk of bridge structures, which are vital for lifeline routes. A closure of a bridge can lead to substantial consequences for the society. If in a critical location of the transportation network, its failure can cost much more than itself, as in the case of Moranda Bridge. Nowadays, performance-based earthquake engineering methodologies aim to design the structures with a predictable and desirable performance. They can express seismic risk meaningfully to decision makers, who can then use such information to allocate the limited resources efficiently for disaster preparedness activities, such as retrofitting of structures at high risk. In this regard, economic loss is a metric commonly used, since it can also be used to set regional or structure-specific premiums with a reasonable rationale for insurance. For buildings to facilitate such a methodology, a formalized guideline, FEMA P58, and associated software tools have already been published. But as far as bridges are concerned, there's no consensus on a unified comprehensive framework to objectively evaluate both components of losses together, which could be very important, as we have just seen. And most of the previous efforts were on the direct loss evaluation, and they always remained at the research level. Moreover, the influence of different aspects concerning the contributing factors to seismic risk has yet to be understood sufficiently. With this in mind, throughout the thesis, my general scope was to develop an integrated framework and associated software tools to objectively quantify both loss components at a component level for bridges as a part of a road network. While doing so, within specific chapters, I carried out numerical investigations to evaluate the influence of specific aspects related to hazards, soil conditions, vulnerability, and exposure on the risk metrics, such as expected annual loss. And the bridges of interest were typically highway bridges, as seen in this figure, having multiple spans with varying lengths. The deck comprises reinforced concrete slabs and pre-stressed girders, whereas the piers have reinforced circular solid sections. Among others, several types of damage mechanisms were commonly observed in these structures, which can lead to the complete failure, such as superstructure unseating, and a pier failure. Or sometimes they can just lead to bridge functionality loss, as in the case of bearing dislocation, shear key damage, pounding, abutment rotation due to the settlement of backfill soil. In the subsequent chapters, to evaluate the losses for the bridge structures at a component level, I essentially adopted the PBE methodology, also considering some of the damage mechanisms that I just have shown you. It is a well-known four-stage procedure, as we see here, and in this process, the damage could be quantified rather simplistically at the structural level by utilizing the bridge fragility curves, or comprehensively at the component level using component-specific damage models. Following this, the losses are computed with a simple or comprehensive consequence model. Regardless of the approach followed, though, the structural response is typically estimated through dynamic analysis, which requires as a fundamental step the selection of suitable set of ground motion records. In general, especially in regions of inadequate seismic networks, it is unlikely to acquire regional recorded ground motion sets from strong earthquakes to provide meaningful statistical data in the structural analysis because these events occur with low frequency in the nature. As such, records of worldwide events with comparable seismological parameters are utilized in practice. Another alternative is to use regionally simulated records for such engineering applications. And previous studies evaluated the validity of simulated records only for scenario earthquakes and only in terms of structural response. Here, on the other hand, for the first time, PBE methodology is adopted and to make a broader comparison between in terms of both structural response and risk metrics. As a dynamic analysis procedure, in addition to computationally more demanding multiple step analysis, cloud analysis is employed. The latter is more suitable for working with unscaled records. However, the choice of records is much more influential and decisive. Thus, the simulated records could be particularly useful in this case. And the ground motions were simulated using stochastic finite fault modeling. Within this modeling approach, a large rectangular fault plane is discretized into subfaults, and each subfault is considered as a stochastic point source. A large simulated ground motion database covering a wide range of magnitude distance pairs and the two site classes was generated for Düzce city in Turkey using regionally validated simulation parameters. Initially, an existing bridge, namely the Çingoli Bridge, was assessed. It is discontinuous and has both in plane and out of plane curvature, making the bridge very irregular. And the superstructure is composed of 14 spans supported on metallic bearings. Then a bridge portfolio, which was produced from statistical characteristics of a portion of the Italian roadway stock, was assessed. The portfolio is composed of 50 straight continuous bridges with single column piers. And unlike the Çingoli Bridge, pier-to-deck connections were established through non-sacrificial shear keys. The numerical models were always developed in the open seas environment. And due to dynamic characteristics of the bridges, average SA was selected as an intensity measure by considering appropriate period range separately for bridge portfolio and Çingoli Bridge. Then probabilistic seismic hazard analysis and disaggregation analysis were performed using OpenQuake engine. While doing so, a significant effort was dedicated to developing an open source Python-based software tool, which I name EasyGM, and it can be easily used for ground motion record selection and processing. Any user who is willing to use it can automatically select the records matching the target spectrum, retrieve them from the online strong motion databases, and then scale them. The condition spectrum as the target can be created utilizing any ground motion model available in the vast OpenQuake hazard library. And upon performing the PSHA and disaggregation analysis with the OpenQuake engine, the tool was used for hazard consistent record selection to carry out the multiple stripe analysis in this study. And it was found that the error in matching between the spectra of simulated records and the condition spectra was usually higher than in the case of real records, and it got even larger when the selection was performed at the higher return periods. And the tool was then later used to select unscaled records for cloud analysis. The records were selected to match the distribution of a scenario earthquake spectrum. Although this time the simulated records seemed to be better matching the target, the errors in both cases were minimal. To obtain the engineering demand parameters of interest for quantification of the damage, the dynamic analysis procedures were carried out only in the transverse direction of the bridge. And the damage quantification was then carried out. In the case of MSA, record-to-record variability, modeling in uncertainty, and uncertainty in the capacity were considered, whereas in the case of cloud analysis, only record-to-record variability was considered. As cloud analysis allows only the use of structural level approach, component level approach was not considered in this case. And as shown here, while computing the losses at the structural level, component damage ratios and the bridge replacement costs were used to estimate the expected direct losses at each intensity measure level. On the other hand, comprehensive consequence loss model relating the repair costs to damage in each component were used for estimation of losses at the component level. Integrating the hazard curve over the expected losses or the mean loss curve, the expected annual losses were obtained as the end result, which are direct in this case. Additionally, a comparison of direct seismic demands were made in terms of residuals, bias, and statistical hypothesis testing. Regarding the p-values, if it is above 0.1, we cannot claim that the two sets of maximum pre-drift ratios are different than each other. And if the bias and the residuals are close to 0, meaning that the two sets actually are very similar to each other. Looking at the results for the Chingola bridge, in the case of MSA, p-values, residual distribution, and model bias confirm that at higher return periods, the demands significantly differ. The structure seems to be more fragile if simulated records are used, a higher expected losses obtained using simulated records at higher periods. Yet the expected annual loss values are still very close, as we see here. And in the case of cloud analysis, the similar observations were made. The demand values were not that significantly different based on the statistical test. Bias and the residual median values from both were very close to 0, even if the standard error was relatively high. And as before, when simulated records were used, similar fragility parameters, theta and beta, were obtained. Likewise, the expected annual loss ratio was slightly higher this time. Looking at the results of bridge portfolio in the case of MSA, the similar observations are made. The residuals, bias values, and the p-values confirm that the seismic demands differ only in some cases of higher return periods. As before, when simulated records were used, even though structures seem slightly more fragile, both fragility curve parameters seem sufficiently close. Likewise, on average, regardless of loss assessment approach, the expected annual loss values were sufficiently close. The results look even better in the case of cloud analysis. On average, the resultant dispersions of fragility curves were lower for simulated records, whereas the medians are sufficiently close. On average, the difference in terms of expected annual loss values were minor, and the null hypothesis was never rejected only for 4 of the bridges. On average, the model bias values were close to 0, also verifying the similarity of the demands. Similar observation made for the residuals. And all in all, it was not possible to select the hazard-consistent simulated record sets matching condition spectrum at high return periods with small error, making their use difficult for MSA. Regardless of the dynamic analysis procedure, in general, seismic demands obtained using simulated records were similar to those obtained using real records, especially for bridges with relatively short periods. Likewise, on average, regardless of the estimation approach followed, the difference between EAL values and fragility curve parameters were minor. However, as the periods of structure got larger, the differences also became more significant. And finally, outcomes of this chapter show that the simulated records could be more suitable for application in which unscaled records are preferred. In the case of cloud analysis, lower record-to-record variability observed, while the median of fragility curve and expected annual loss were sufficiently close to those obtained using real records. As far as local site effects are concerned, for practical reasons, they are conventionally incorporated through site VS30 values. Moreover, typically soil structure interaction effects are ignored in the risk assessment applications. So the goal of this chapter is to compare the difference between the conventional approach and more refined approaches of increasing complexity level. Accordingly, 4 approaches were adopted and compared in this chapter. In the first one, which is the conventional one, the site amplification relies on the selected ground motion model and the site VS30 value. The piled foundations are assumed to be fixed bases in the numerical modeling. And in the second approach, it incorporates the foundation flexibility by utilizing PY models in accordance with the local soil properties along the piles. Thus, it is more defined. However, the same set of records for the previous approach is applied uniformly as the acceleration time series along the piles on the PY springs. Thus, the site amplification is still simplified and there is no realistic compliance between input motions and foundation. The third approach incorporates the local site amplification in a more refined way and estimating from one-dimensional site response analysis that are carried out on a set of records for a rock site. The resultant acceleration time series obtained at the ground level upon performing site response analysis are applied to the fixed base numerical models, ignoring the foundation flexibility. And in the fourth approach, the depth-varying displacements obtained from the site response analysis are applied along the PY models, hence combining both site analysis and soil structure interaction refinements. Even though this approach accounts for inertial and kinematic interaction realistically, it is costlier than others in terms of computational time. Therefore, unlike previous chapter, the scenario-based loss assessment was carried out with the goal of obtaining extracted scenario losses in the end, which are direct in this case again. 2 site classes and 2 soil profiles per class were considered in this study, and 3 different record sets were selected for soft, stiff, and rock sites. The first 2 sets were directly used in the structural analysis since the amplifications were indirectly considered in the target spectrum, which is created using the site VS30 value as input for the selected ground motion model. On the other hand, the third set was used in site response analysis, and the amplified time series for each soil profile were employed. For both site classes, the resulting mean amplifications differ very significantly than the ones from the ground motion model. 4 continuous bridges were analyzed in the directions which are unfavorable for them. And in the case of flexible bases, the PY models were developed as demonstrated here. In order to account for pile group effects, ultimate strength of PY springs were reduced by group efficiency factors. And in the case of fourth approach, during the analysis, the ground displacements were applied at the free end of PY springs after obtaining them from the site response analysis at each corresponding layer. The fundamental periods of numerical models we see here, and the sites were estimated for the comparative purposes later on. As explained earlier, in addition to the conventional approach, utilizing the different site characteristics, 3 different approaches were considered that are highlighted using different colors here were employed. And initially, the similarity of the demand to capacity ratio values obtained with different tested approaches with respect to the conventional approach was statistically tested. Except for bridge 1, the p-values indicate that the seismic demands obtained from the conventional approach are apparently statistically similar to those from all other considered analysis cases. Furthermore, in line with the observed p-values, the residuals for the bridge number 1 were significantly lower than 0, regardless of the site classification for the cases where site response analysis was carried out. And this outcome is expected as the site amplifications provided the ground motion model was significantly higher than those obtained by the site response analysis at the fundamental period of the structure. Moreover, it becomes obvious that introduction of foundation flexibility alone does not impact the demand to capacity ratio values significantly, and even if they affect, they are in general beneficial. And when we look at the direct losses, the picture for the other cases becomes more clear. Except few cases, in general, it was seen that the losses tend to be larger if site amplifications obtained from site response analysis are relatively larger or the period of the structure is relatively close to the site fundamental period. On the other hand, it could be seen that the soil structure interaction effects are mostly beneficial. Nonetheless, in some cases, the losses got larger as the period of the structure shifted towards the site period's proximity. To conclude this chapter, it can be said that the conventional approach seems to provide reasonable results and thus might be used for large-scale applications. Yet, if it is possible, it could be worthwhile to check closeness of initial periods of both site and structure before using it, as the site amplification could be very significant than anticipated. And the site amplification could be quite different if estimated from the site response analysis and ground motion models in the particular case, in the particular case of the ones from the selected ground motion model were over-conservative at the relatively high periods. And finally, the foundation flexibility and the soil structure interaction effects were found beneficial in the absence of significant resonance effects. And when we look at the older highway bridges, we often see the thin, unreinforced neoprene bearings, such as this one. And such bearings are usually single-side bonded and subjected to high compressive stress. Under lateral load, they behave elastically until friction force between rubber and concrete is reached, and then start sliding as we see here. There are two key parameters to mimic such behavior, which can be costly to determine through the tests. And the first one is the shear modulus of the rubber, which can take a wide range of values due to ongoing time-dependent changes. And the second one, is the friction coefficient between rubber and concrete, for which, again, a myriad of recommendations could exist. Therefore, in this chapter aims to understand the role of these significantly varying parameters in the direct risk estimates before allocating further resources to estimate them more accurately. The existing bridge was first assessed using a simplified modeling approach, which is commonly used when an information is not enough and computational resources are low. This is just a connection with a pin connection, actually. Then it was assessed using a more refined approach, but neglecting the presence of the non-sacrificial shear keys on cap beams. And finally, it was assessed using the same refined approach, refined model, but with the presence of the shear keys. In order to cover a wide range of parameters, 100 pairs of samples were generated using Latin hypercube sampling. And as seen, the dynamic properties of the models differs slightly due to the differences in the shear modulus of the bearings. And differently from others in this chapter, the ground motions were employed in both longitudinal and transverse directions. Thus, record sets were selected according to this. In addition to the direct expected annual loss, the mean annual frequency of collapse was also computed. And accordingly, the damage models and the consequence models for the bearings included in the assessment procedure as a difference. In general, both loss and fragility curves obtained using both refined models agree with the one from the simplified model. Yet the simplified modeling seems to be, in general, conservative, especially at lower intensity measure levels. Moreover, curve-to-curve variability seems to be larger for the case without shear keys. And when we examine the risk metrics against investigated bearing properties, we see that the friction coefficient is highly influential, yet the shear modulus has no direct consistent impact on them. Basically, we cannot see any trend there. And even though simplified model mostly yields conservative results, it could be unconservative in terms of losses for the high values of friction coefficient. Moreover, it was seen that the losses and collapse risk tend to be higher as friction coefficient approach to lower bounds, meaning that for bridges with insufficient seating length, the simplified model could be in fact unconservative, also at the lower friction coefficient. In this case, the sufficient seating length was provided to the bridge, or it was already there, so there was no greater risk. To conclude, I can say that simplified modeling is rather conservative, hence acceptable, except for high friction coefficient values, and also potentially for very low friction coefficient values if unseating length is insufficient and shear keys do not exist at the cap beams. Moreover, time-dependent changes, such as aging for the bearings, such type of bearings, is not big of a concern as we see, yet more efforts need to be put in understanding of the friction coefficient and which value to use for such bearings, as it has significant impact on the risk metrics. And building upon the previous efforts, the final chapter introduces the integrated assessment framework, which computes the losses at the component level and the software tools that can be used at various stages of it. And it is essentially the same as the PBE approach, but it has one external step, that is the network analysis necessary for computing the daily indirect loss associated with the bridge functionality. And this information will be used to estimate the indirect losses later on. Daily indirect loss can be expressed as the difference between the daily operational costs obtained for the baseline traffic conditions and the modified traffic conditions due to the seismic damage on the bridge. This information is utilized at the loss analysis stage for the bridge being assessed. And even though the focus here was on the seismic hazard, in fact, the framework itself can be adopted for other types of hazards as well, upon, of course, implementing the necessary modifications in the stages other than the network analysis. The whole seismic risk assessment framework can be applied for the bridges of interest here through open source Python packages which were either already available or developed within the thesis. And in particular, EasyBridge package was developed during the thesis with a significant and continuous effort for the structural analysis, damage analysis, and the loss analysis stages. So the package, in fact, provides two main tools to the user. The first one utilizes OpenC's engine for structural modeling and analysis. Through automation, it makes the numerical modeling for of the multi-span RC bridges extremely fast, which is something essential for analyzing significant number of structures. And the second one is the risk calculation tool. It utilizes the site hazard curve and the outputs produced by the previous tool to compute the seismic risk metrics for the bridge being assessed. The computation of the indirect losses within the tool is the same as in the previous chapters at the component level following the FEMA P58 procedure. For indirect losses, on the other hand, the number of available crews for repairing and daily indirect loss information for the different bridge functionality categories are required. Functionality category that I'm talking about relates to seismic damage to the traffic flow capacity and the free flow speed reduction on the bridge. Accordingly, in addition to fully operational network model, the network analysis is carried out for the three functionality category after applying the corresponding reductions on the link that represents the bridge in the road network model. Then the tool uses the consequence models to determine the durations when the bridge is at different functionality categories throughout the repair and the reconstruction activities. In the case of non-collapse cases, aside from the repair times, the duration passed before the start of repair activities are also considered. Such duration refers to the activities carried out, such as logistics and engineering design. To demonstrate the importance of indirect losses in the risk prioritization, the proposed framework was applied to the case study network. As the information was not available for the bridges in the network, let's say the modeling information actually, the bridges from the previous chapters were randomly distributed while respecting the lengths of the actual bridges. As it is seen from these figures, the bridges are located in different parts of the road network with different hazard and also with a different traffic demand. And for this purpose, for each bridge's location, different suites of records were selected, and bridge-specific period ranges were used both in the computation of intensity measure, which is average SA, and to determine the matching range while doing the record selection. And let's take a look at the results for the same bridge when it is located in places with different hazard and different traffic demand. We see that even though different record sets are used for the assessments, the vulnerability of the bridges are almost identical in this case, which is most probably because basically the bridges are located in the same seismic region, and just they're farther, some of them are farther from the faults and some of them are maybe closer to those faults. However, more interestingly, the total losses obtained for the bridge when it is located in a lower hazard site was significantly higher. This clearly emphasized the importance of indirect loss consideration in the risk prioritization. As such, when we look at the results with a broader view, it is seen that direct expected annual losses are greater for bridges in high hazard regions, but the indirect counterparts are greater for the bridges with high traffic demand as expected. And naturally, the same is true for the expected annual loss ratio. And the picture clearly shows that the importance of bridge could be significantly different if it is determined based only on the direct losses or only on the indirect losses. Moreover, in this case, it is seen that at the network level, indirect component of the total expected losses was higher. All these show that in the case of bridges, to be able to use expected annual loss as an objective risk metric, both loss components need to be included. As such, total expected annual losses were obtained by proposed framework, and it can be also then used for the risk prioritization of the bridges in the network. So we did, I compared the EAL-based ranking obtained with the framework obtained with the framework with also the recently proposed risk prioritization guidelines in Italy. And it was seen that the original guidelines provide very conservative results in terms of seismic risk. A saturation at the maximum score was observed for the simply supported bridges in particular. On the other hand, the resolution of the results seemed to be improved with the modifications recently proposed by Abarca 2022. Even if the dispersion is relatively high, in this case, in the second case, the general trend between EAL-based ranking and the seismic risk score was observed, and meaning that the scores tend to be higher for bridges classified as high priority based on EAL values. To conclude this chapter, that high hazard does not mean high seismic losses, and indirect losses could be still high. The relative importance of the bridge can be underestimated if indirect losses are disregarded and discarded. Thus, both direct and indirect components should be evaluated while evaluating the seismic risk of the bridges as part of a bridge network, road network. And the EAL-based ranking found efficient for risk-based prioritization since it can be used to identify the importance ranking of bridges in order. For computation of the EAL, the proposed framework can be used. However, it requires, as we have just seen, significant amount of information. Thus, EAL-based ranking can be alternatively used as a benchmark to calibrate or evaluate the simplified seismic risk classification approaches. And the recent Italian guidelines were hard to use from quantitative point of view and the conservative for risk prioritization, as the saturation at the highest seismic risk score was observed, especially for structures with an isostatic scheme. To sum up all I have done throughout the thesis, I developed an integrated seismic loss assessment framework for bridge-specific applications, incorporating the probabilistic estimation of the indirect economic losses along with the direct counterpart at a component level. And I also, additionally, open-source Python-based software tools I developed to facilitate the framework's application on a large scale. Of course, the software and the framework needs it has a lot of limitation, and there could be potential improvements on it, such as including bond slip in the numerical modeling, which was quite frequently observed in the old bridge structures actually, but I couldn't have time to analyze it in my cases. And in the chapter 3, we basically saw that although stochastic method has some limitations, when we use the records using this methodology and the regionally validated parameters, it can be a good alternative for risk assessment, in particular when we want to employ unscaled records in the nonlinear time story analysis. And the conventional approach in the 4th chapter is found reasonable for large-scale seismic risk assessment applications on bridges with deep foundations. However, the uncertainties associated with the simplifications made in the numerical modeling must be kept in mind. And on average, we see that soil structure interaction effects seems to be beneficial, yet local site amplifications could be more significant than anticipated. And finally, and the rubber shear modulus we see in the chapter 5 did not significantly impact the considered seismic risk measures, making the time-independent changes such as creep and aging less of a concern for this type of bearings. Nonetheless, it was advised that prior conducting vulnerability assessment studies, careful investigation and estimation of the coefficient of friction between rubber and the concrete should be carried out. And coming to the last bullet point, the observations indicate in the chapter 6 that both direct and indirect losses need to be computed for the objective evaluation of seismic risk. And high seismic hazard does not necessarily mean higher overall economic losses. And yet, the strategic importance could be more significant parameter. And thank you for listening.
Thank you, Volker. Let's start with the questions by the evaluation committee. Walter.
Okay. Just thank you very much for the interesting presentation. A couple of curiosity and some general question, really general. The first one is when you evaluated the indirect costs, I have not understood well which kind of indirect cost you include in the calculation. Can you explain me better? Because there are a lot of kinds of, and really not easy to calculate them. So can you explain me how it works?
Of course, that's a very valid question. In fact, it's a limitation, or let's say further improvement that needs to be done. In this case, the idea was just to show how such a framework can be applied. So I considered only a portion of indirect losses, which could be much more than this. And the portion that I was showing is just losses that comes from the users in the road network. As they drive, as the vehicles are driven, you of course spend obviously gasoline, and the people go to places later than expected. Due to this, we anticipate some sort of losses, indirect losses. And these two actually were the ones that I considered in my study. Actually, this equation, which we calculate daily operation costs, is already there, and the idea was not new actually, but I just extended it to consider more the framework at the component level, and also considering the damage limit states other than the collapse.
Okay, so you consider that the cost due to the more time that people spend on the road network due to jams and so on, for example?
Yeah, exactly.
And what about human life? I mean that probably with a different kind of traffic distribution there can be more deaths because of accidents and so on, for example.
That is true, but to my knowledge, at the moment, there's no possibility, or if there is, I do not know, to be honest, to account for potential accidents that can occur in the traffic if we close another bridge. But basically, when you do the network analysis here, we account for the traffic jam, which is going to occur due to the closure of the bridge or due to the partial use of the bridge.
Another question, you have to take into account also different functional category, in the sense that if you have alpha lines open, for example, on a highway, it means that you have also you can have jams on highway also. You can have also a different distribution of traffic on highway and on the secondary network, and so it's not easy to understand how all of this happens when you have a reduction of functionality on the roads. I think it's an interesting problem, but it's not all, as you told before, completely resolved at the moment. Another question, it's just, I don't know how to say, it's not completely correct, but I would like to understand how you answer me. If you have a bridge in a network, no? And you have a bridge lifetime and so on, when you evaluate the risk, do you think that it's higher the risk or the cost connected with these risks to retrofit this bridge, or if you leave the bridge unretrofitted and you accept the risk, this risk is higher than the risk connected to the to the period of not functionality of this bridge. I don't know if I expressed myself. You have two solutions. I'm the owner of the bridge. I can leave the bridge like now. It's vulnerable. You have a certain time, a certain level of vulnerability. And we accept the risk. You evaluate this risk, seismic risk, on the time for its lifetime. The second solution is, no, I repair the bridge, I retrofit the bridge, I adequate to the standards, so I increase, but I have to make works. It means that for a long period I have a loss of functionality. I have to deviate the traffic on the secondary roads, and it means that I have an higher risk because of works. So if you compare the two risks, do you think which is higher of them between them?
Well, that's a good yeah, no, I understand. That's a good question, actually. Well, that is true. I mean, if that is basic cost-benefit analysis, what you're asking, and it really depends. To be honest, I have no expertise in retrofitting of the bridges. To be able to answer what you said, we actually need to look at what people, how much time spent on retrofitting the structure itself, and how much time they spent when it is damaged after an earthquake. So this requires actually investigation or survey through people who work in the industry. Otherwise, it could be rather difficult to estimate. Even the values that I was using here to estimate the repair times and etc., they're kind of estimations that I come up with by talking to people and etc. So that is why, to be able to answer that, actually, we need to look at what is going to happen. But in my feeling that for some damage limit states, let's say, if you need to change a pier after an earthquake, that is a long operation, okay? And I believe in such scenarios, let's say, if we see that losses or whatever the risk that we are calculating exceeds certain threshold, we may try to say, okay, we may say that, okay, if my bridge is going to enter this damage limit state, I'm going to wait much longer than before, and thus maybe just waiting during the retrofitting procedure could be beneficial in that case.
And the last one, it's where we are in the bar. If you have to analyze other risks, because you made a really nice work on seismic risk, EL, and so on. But you have to make the same, similar, if you make a similar approach for other risks, for floods, landslides, for how to say, for the traffic, or for exceptional loads, or for the risk connected to the quality of the road platform, that is also the quality and type of flat. What do you think about the balance of these risks? Which is more relevant if I am the owner of the road? First of all, what I have to do?
Well, it's not an easy question.
No?
I have not expertise, of course, in other hazards. But I believe if you can use such framework, also implementing the other hazards, because systematically it is the same, right? We have the hazard part, hazard analysis. It could be any hazard related to flood. You need to just estimate the likelihood of it with the analysis. Then you have the structure analysis part. Of course, I haven't analyzed the structures for the flood, but I believe the idea is the same. You just look at where the damage occurs for certain type of flood. And in the case of damage analysis, you again do the same. You look at which components could be potential damage by the flood, and you evaluate the damage based on what you obtained from structural analysis. And in the loss analysis part, again, you need to obtain similar consequence models, which are this time particularly for the damages which can be for the components which can be damaged by the different hazard. But of course, this requires a lot of time. I'm aware of that, and that's why I guess we are doing research. And of course, I cannot answer really how to evaluate the risks, and this is a very thorough approach, and at the moment I don't think we can do it this way. That's why the simplified procedures like the guidelines, Italian guidelines are handy actually. But my idea, as I just explained, my reasoning, we can use these guidelines, but maybe it is worthwhile to improve them by looking at the cases where we use the more refined approaches such as this one. And then we can use these guidelines to compare the risk of any hazard.
Okay, thank you.
Ladies first. Let's say ladies first. Okay, thank you. I only have a minor question that I'd like you to reply to. In the framework of the assessing the modification to the traffic, you mentioned the functionality categories, and I'd like to know what's the relation between how do you attribute those classes based on the damage assessment? So when is actually that you consider a reduction in the weight restriction, or one lane is closed or the bridge is closed?
So how relate these functionality categories?
Yes, how do you attribute that to a bridge based on your damage assessment?
Yes. So yeah, of course, there are some assumptions, and I think sorry, I forgot to put the table. Actually, apparently I skipped a slide, which I thought it was there. There was in my thesis, there's one table actually where you look at in the table, you just look at the components and the corresponding, for their corresponding damage limit states, you look at the corresponding functionality categories. So basically, let's say, if your pier is at damage limit state 3, your bridge is going to be in functionality category 3 because the pier needs to be replaced. And you cannot do it without closing the bridge at all. But for some operations, that's actually another assumption that I have to make. Maybe it is not really true. For some other operations, like let's say, you just have a spalling in your concrete and you want to repair it after the earthquake. And in these cases, you just attribute a lower functionality category to bridge. You may not need to close fully the bridge itself. You can just close the bridge for a certain period, or you can partially close the bridge. Just reduce the number of lanes which are being used. You can use the speed reduction and etc. So that is how actually you relate the damage to the functionality category itself. And while doing this, of course, there are some assumptions. How you come up with the functionality category for the bridge, that's another question, because you have many component damage, and how you decide on the scheduling of the repairing activities. So in my case, I thought engineer will be pragmatic, and he will think that, okay, my bridge is damaged, I have several components which requires repairing, and I need to repair these components in certain order, and to decide in which order, engineer most probably will think that how can I repair it as fast as possible, and how can I repair it? as efficiently as possible, which means that if certain type of damage is more critical and it puts the bridge into more greater functionality category, I want to repair this one first, because this way I can increase the functionality of my bridge sooner. So, and that's how I actually come up with the repairing schedule while doing the assessment.
Okay, thank you. So if I understand correctly, in your case, it was based on expert judgment from your part?
Yes, how I relate is mostly on expert judgment and let's say engineering judgment. Yes.
Okay, thank you.
Okay, thank you for your presentation. The framework is really interesting, and I found very impressive the incidence of indirect losses in these cases. And so my first curiosity is about some, if possible, a comparison with real cases. So did you validate somehow with some real case, if it is possible, your estimate about the indirect losses with real cases? Do you have data about this point?
Again, this is a future it's a limitation that I have at the moment, and it is definitely required. I mean, but also the validation is not easy. I don't know if we can usually have such kind of data easily, first of all. And in this actually study, since I was doing time-based loss assessment, I was computing the expected annual losses and making the comparisons in that way. In validation, of course, we need to validate this kind of procedure also for the scenarios, but we can still use the same strategy to compute the consequences for the given intensity measured level. But at the moment, I couldn't do it, and I don't think it is very easy to do soon. And I know that it's a limitation, it's a big limitation. But I believe it is, for many cases where when we carried out the loss assessment, it is not an easy thing, I believe.
Yes, validation can be very hard in these cases. Another curiosity about the hazard estimation, hazard assessment, maybe you already told this about this point, but I didn't understood if did you consider the spatial variability in seismic hazard for a network like actually? Yes, okay, and also. The question is about the spatial variability and also about the possible variation in local amplification effects from peers to peer. Did you consider also this kind, or it is possible to implement eventually also this this issue in your framework?
Well, again, considering spatial variability in such kind of time-based assessment is not, I think, possible really, because in this case I'm trying to evaluate the losses for specific bridges, like considering the time, overall time that is we are going to observe. And that's why in this case, actually, I know that it is very related because earthquake doesn't have effect on a single location, it affects all the locations, but in that case, we need to carry out the scenario-based assessments to account for it, to my knowledge. And that's why in this framework, I was trying to somehow compute the risk of structures or the bridges, considering the overall lifetime or the what's going to happen in the next time interval that we have. So in this case, we didn't, of course, I didn't account for the spatial variability. And in the case of also the soil structure interaction analysis, yes, it is another topic needs to be studied. But the problem is I did not have a real case bridge where I have all the information regarding different soil layers and etc. So in this case, I just assumed that the soil profile is the same along the bridge itself, and that's why spatial variability was not there, but the focus was actually related to site amplification. So that was another reason I didn't want to go into the spatial variability issue.
Okay. Just a last question about the modeling of peers in particular. I saw only a picture about the fiber approach, modeling approach on force-based displacement or the displacement-based approach, I don't know. So just, okay, the flexural response of the peer. Do you think it can be, or do you have already done it? It can be important to model also a modification of such response in case of short peers, for example, when the shear deformability or shear response, shear strength also can be important in the response of the peer.
Of course, that is very important, but actually, even though it looks like I didn't account for the shear damage in the piers, I'm just trying to find the correct slide. I do account for it because I use the damage models which also actually evaluates or gives you the shear capacity of the bridge in terms of pier drift ratio. Oops, I think it's here.
So with the drift capacity that depends on
so here, for example, the dashed line you see is the shear capacity. It explains the damage model explains the shear capacity as probabilistically based on the pier drift ratio that you see here. So while doing the damage quantification, yes, I do account for the shear failure mode, but within the modeling, I not particularly model the shear springs, but I accounted in the damage quantification part, so I believe in that part, if these damage models are reliable, which I think quite reliable because they come from thorough study, we already account for the shear damage. So I do not know to what degree adding extra shear springs, which are brittle, will change the result that we have.
Okay, thank you.
Okay, thank you very much for the questions. The discussions today are excitingly long, so again, we're out of time. We don't have time for questions from the audience. Thank you, Volkan, once again. And we move to the last presentation of today, Luis Alvarez. Luis has already defended his thesis in France because his PhD is part of a co-tutel agreement, but still he's going to present us his work, 3D stochastic ground motion simulation for structural response analysis. Luis.
Good afternoon, everyone. My name is Luis Alvarez, as Ricardo just mentioned, and this afternoon I would like to present part of our work titled Improved 3D Stochastic Ground Motion Simulation for Structural Response Analysis. First of all, I would like to thank you for being here, for your attention, and to the organization for inviting me to present at the seminar. It's always nice to come back home and see so many familiar faces. So the agenda of our presentation is rather simple. We have 4 points. We're going to go into the introduction to talk about context and motivation. Then I will present to you very briefly, let's say, the 3D stochastic ground motion simulation method that we have proposed as part of the thesis. I will then present 2 validation cases, applications and verification cases, And finally, I will talk about conclusions and future work. So first of all, introduction. How did the project come about and why are we doing this? So basically, as Ricardo mentioned, this project was developed as part of a joint PhD project with 3 partners, namely IOSS Pavia, represented by Paolo Bazzurro in the back, Université Gustave Eiffel, represented by Fabian Bonilla, and EDF Research and Development, represented by Gloria Senfot and Irmela Sentner. So basically, the importance of this work is rooted in the necessity for acceleration time histories for seismology and earthquake engineering applications. Now, time histories, or records as we often call them, are complex time series representing earthquake ground motion at a given site. I guess I don't have to show an acceleration time history to an audience full of earthquake engineering seismologists, but you have one to the right in which you see a couple of its characteristics. You see its peak ground acceleration here at 0.2, you see the arrival of the S waves, but you could also look further and you could see the different phases that act, the different frequency content, the non-stationarity in time and frequency domains, and so on and so on. Now, an example of the uses of records is the case of seismic risk analysis, where basically records provide the link between seismic hazard and structural response. Here, records are selected to collectively match the hazard, obtained distribution of a condition in intensity measure or vector of intensity measures. In the figure, for example, a set of records is selected to match the conditional spectrum at a site of interest to analyze the structural response of any structure you would like. Now, despite the relevance, record databases are scarce, and so many scenarios of interest for seismic engineering and seismology applications are missing. For example, you see to the right a figure where I show the pairs of all the events contained within the NGA2 database, and you see that there is a white spot where you have no points, and it's mainly for short distance, high magnitude events. To face this challenge, one of the proposed actions is the consideration of simulated earthquake ground motions. This is motivated by the continuous improvement in the understanding of the earthquake phenomena source attenuation site, but also in the by the continuous growth of computational power that we have available nowadays. Now, without other distraction, let us get into the matter. I would like to present to you now the 3D stochastic ground motion simulation method. But first, we will talk a little bit about the methods, what they are, how can we place the one that we're working with now in terms of the literature, and what is our proposal, and basically what has to offer and what's different with respect to other proposals out there. So, overall, you might say that there are three categories, let's say, of earthquake ground motion simulation methodologies. The first one, which is often called deterministic or physics-based, explicitly models the rupture and the wave propagation and requires extensive information for the characterization of the model. Also, the frequency band at which you can simulate, it's, let's say, determined by the mesh of your propagation medium and of the rupture, and so a lot of the applications of this type of methodologies result in very limited simulations in terms of high frequency content. The second one, it's the stochastic ground motion simulation methods, which basically model ground motion by a convolution of white noise and a simulated ground motion spectrum. So basically you have a mean of what it looks, a ground motion spectrum, and you add some noise so as to give the random phase of the random phase of the acceleration time history, let's say. Finally, you have a third, which is basically the union of these two. You have deterministic methods to model the low frequency content, and you have stochastic methods to model the high frequency content of the ground motions. These obviously are also subject to the limitations of both methods. Now, because we're interested in a method capable of generating large number of scenarios at low computational cost in order to explore the uncertainty in ground motion amplitude, let's say ground motion, sorry. We focus our work in stochastic methods. Now, well, they are here. Sorry, I don't see the screen. This is part of the show. I'm coming. This is part of the show. So basically, I just described the main methods that are out there, let's say the main categories. And I just said that we were going to focus on stochastic ground motion simulation methods because basically they are performant for a range of frequencies that we want, and they're computationally efficient, let's say. So if we go into stochastic methods, now, yes, perfect. You see that there are two other, let's say, subdivisions where you have engineering or site-based stochastic ground motion simulation methods, in which basically you add a stochastic process to a ground motion spectrum at an area, at a site of interest, let's say, with no physics involved. Let's say you don't have a model to, let's say, describe the source or the attenuation or any other of the phenomena that describe ground motion in the real world. And you have a second type of stochastic methods that is called, or is often referred to as seismological or source-based, in which you construct the Fourier amplitude spectrum of the simulated ground motion, and then you inject the, let's say, the random phase by considering Gaussian white noise, let's say. Now, because the focus of this work was to have a physically, let's say, sound ground motion simulation methodology, we will focus our attention into the latter, seismological source-based stochastic ground motion simulation methods that I will just call stochastic methods because we need to finish today. Now, how do they work? Basically, you have different steps, sequential steps, in which you first have Gaussian white noise of finite duration. Basically, for each time step, you sample a normal random variable, and then you have something that looks like here, the picture. Then you use a modulating time function so as to give it the shape that we normally see in acceleration ground motion time histories. And then you go into the frequency domain. When you go into the frequency domain, you convolute this Fourier amplitude spectrum of the modulated white noise with the simulated ground motion spectrum that you have created by considering models for your source, your propagation, and your site. And then basically you come back into the time domain so that you have a time history, all right? So how did this look in terms of the literature, and how did we see this evolve? Stochastic methods, stochastic source-based methods were basically, let's say, born from the pioneering work of Aki and Brun in the late 60s, in which they described the model, the source spectrum of the model with a coin source, with a frequency corner, let's say. At the end of the 70s, Hanks and his colleagues used it to simulate PGA. Later in the 80s, Bohr used it to derive acceleration time histories with a point source model. And then in the 90s, you had the extended fold source model, where you had point sources put together to model an extended fold, let's say a finite fold source. In 2005, Motasedian and Atkinson basically proposed a finite fold energy minimization model so as to make this source model independent from the discretization of the source. And more recently, in 2016, a group of Chilean researchers proposed a 3D stochastic ground motion simulation method by including the model of the P and SV waves into, let's say, into the recipe. Before it was mainly SH waves. Now, our proposal, what is it? Basically, it's a finite fold, seismological basis stochastic ground motion simulation method that, as I said before, takes into account what has been built. So we take the most complete model, taking P, SV, and SH waves. We couple it with a simplified propagation of a direct ray into, let's say, a stratified medium, modeling the crust. And then, voila, we have a stochastic ground motion simulation method. However, we have worked into improving this currently existing method by improving the source model. We have done this by taking into account a kinematic source model and a corner frequency model that evolves as the rupture propagates from the hypocenter to all of the finite, say, points modeling the source. We have also enforced the spectral correlation structure, which has been noticed by studying recorded databases, and that it's very important for the analysis of structures, specifically if you are if you're thinking of going into the nonlinear range. So now that I have described it, let's say briefly, I would like to go a little bit further into the specifics of the points of the method and the ones that we have worked the most. Let's say, for example, here we have the simulated ground motion spectrum, which is, as I said before, and it's a very recurrent phrase in my presentation, so I hope you with me. You have the source, here modeled by S. You have the attenuation by A, and you have side effects modeled by Z. When you look into the source model, you are here looking at a finite source model representation, which is constructed by an array of point sources. Each of these point sources will irradiate seismic waves that are characterized by a source spectrum described by a frequency corner. Remember the model by Aki and Brun? Then you're going to go and then you're going to propagate these seismic waves from each of these points into the site where you are observing, or you want to get time histories, let's say, and you're going to model the crust, the crustal structure of your region by a layered model, a 1D layered model, and you're going to use ray theory to propagate these seismic waves from each point into the site. And that way you are going to have an estimation of the time of arrival of each of the waves of each of the point sources. You're going to have an estimation of the incidence angle that will affect the amplitude of the ground motion and the distribution between the different components of the different rays. And you will have, okay, so you have time now. You have the effect of the attenuation due to the path. Finally, if you want, and if you have something available, you can add side effects by convoluting this source and attenuation, let's say, components with transfer functions. Here, for example, I am presenting analytically obtained transfer functions considered or obtained with the Haskell-Thompson matrix method. However, if you have something like, for example, a spectral inversion, you can use those transfer functions and couple it with this kind of methodology so that you have something representative of your site. Now, regarding the correlation structure, recorded ground motion show correlated spectral amplitudes. And this has been seen by researchers because they have looked at the residuals of ground motion models, or GMPs, as we usually used to call them before, with respect to single records. So for example, you compute residual, such as it's expressed here by the equation. It's basically the standard deviation normalized difference of your spectral acceleration at a given period of vibration with respect to the ground motion model that you're using as reference. If you have this, for example here, shown computed for 2 different periods of vibration, if you have these clouds of points computed for a ground motion database at 2 different periods, you are able to compute, let's say, the correlation that it's between them, that exists between them, and you come to what we know as correlation structure models, such as the one, for example, shown here by the black line and reported by Baker and Jerem in 2008. So because we had originally used ground motion, because we have originally used white noise, which is by definition uncorrelated. At each point you are using a different sampling, you have originally the blue line that you see here. You see a non-correlated model. But if you follow the procedure that we have proposed in our thesis, and it's based on the pioneering work of Wang et al., you have a way in which you can inject vectors with the correlation into your simulated ground motion, and then you can basically, let's say, put it there, insert it into your simulations as a post-processing procedure. This has been done in the past. We have extended it to a 3D framework because our method, as I said before, produces 3D stochastic ground motion simulations. Now, to the fun part, applications and verification. We have considered 2 applications that I will present to you. A first one, an earthquake ground motion prediction case, which we often refer to as seismological verification. And then you have the single building risk assessment, which we often refer to as engineering verification. So let's go. So for the first one, for the seismological validation, the idea would be to apply the 3D stochastic ground motion simulation technique for a ground motion prediction case. So the idea would be to sample the uncertainty of the input parameters of a region of interest and then compare to statistical models that will give you something of what would you expect in the area. For this, we will compare intensity measures of interest, such as, for example, response spectrum, significant duration, Fourier amplitude spectrum, and time series. How are we going to compare time series, though? We pulled up a trick here. Basically, we consider our case study to be an actual event that already happened, so that we could have time histories to compare with, and that we can have, let's say, a realization, a possible realization of what would you expect in the area. All right? So for this, we considered 2004 magnitude 6.6 Niigata earthquake. That, I remind you, it's not our target. We're not trying to precisely model that one, but we're considering it as just one of the possible outcomes. And also it gives us the nice feature of having some acceleration time histories to compare it to, which is the output of our simulation technique. We don't output response spectra or significant variations or anything. We output acceleration time histories. So for this, we will look into a set of stations of interest where we will compare our responses. In the figure up to the right, you see the location of the plane of rupture and the epicenter of the actual event that happened, our observed reference event, and the location of 6 stations of interest. These 6 stations of interest were selected because they were most, let's say, close to the actual behavior that our model is trying to represent, namely direct body waves, so no surface waves. This is why we're limiting our hypocentral distance to a maximum of 70 kilometers, let's say. And we are not taking into account nonlinear response of the soil. This is why we're taking, let's say, rigid soils or rocks, so VS30 above 500, to do our comparisons. You have here a description of the site conditions of the sites that we considered. So, okay, now we have our target. We have our ground motion simulation method. The objective of this exercise, as I said in the beginning, was to simulate and see if we could capture the response of what we would expect we would see in this area. So we would like to see if we're able to propagate the uncertainty from input to intensity measures. However, since we're already doing this, we also explored the use of the model to couple it with different techniques for cases, for example, where you don't have information. So we defined 2 main cases here. Case A, which is basically characterized by information from the literature. For this specific application, we considered the spectral inversion campaign conducted by Odd and his colleagues in 2010 and 2011, with over, I think, something more than 78,000 earthquake records from Japan. Here in the figure to the right, you can see a sonification that was part of their work. And then we're going to use case B. Case B is going to be, let's say, a situation where you don't have data and you are forced to extract data from the observations you have at the site, right? So for example, in the figure to the right, you have the description of the events that we use to characterize our simulation method. So in purple, you see here the epicenters of the earthquake scenarios that we used within a generalized inversion, a spectral inversion, let's say, framework, to obtain the parameters that would allow us to simulate ground motions at the area. The idea is that if we remain local, we will be able to capture endemic features that are diluted, let's say, by the larger areas of study that larger studies, such as, for example, Odd consider. To characterize our model, also, as I said before, we looked into the source. Since we're trying to represent the variability, the idea, or our idea, was to simulate a population of earthquake sources. This population of earthquake sources was simulated by sampling the geometry of the source, considering the Wells and Coppersmith model of 1994, and by considering a fixed hypocentral depth. Why fixed hypocentral depth? Because we want to have the same base of comparison with respect to our observed reference event. You see in the figure shown in the slide, the histogram of the length and the width of the fall, and you see that the histogram of the population of sources that we simulated, I'm sorry, I have to be more specific. And you see the vertical line showing the one that was actually obtained from the observed ground motion event, our observed reference. We considered 2 cross-zone models that were obtained for the area based on the inversion, on the low frequency inversion of recordings for this specific earthquake. We have a stepwise model, the Aochi model that is shown here little, and you have a gradient-like model, the Hikima-Koketsu model, that it's shown here in the larger scale. Regarding the time modulating functions, we went a little bit creative here, not only to try to capture the spectral content of our ground motions, but also to try to capture the evolution of the amplitude with respect to time, duration, and some other, let's say, duration-related intensity measures. So what we did was basically we took the modulating before that we used to filter our Gaussian noise, and we played with the parameters, and we compared it to predictions of a valid ground motion model, a GMP. In this case, the Alpha-Hari 2016. So we basically played with the parameters of this function, and these are basically 3. I'll describe them to you. The first one is FTGAM, which basically models the elongation, the length of the window. You have E, which basically gives you the location of the peak of the exponential window. And then you have eta, I'm sorry, it's eta, right, in Greek. You have the attenuation of the modulating function. We basically sampled possible values of these 3 parameters, and we compared it to what a GMP would give for the area, and we picked the ones that would give us the closest, let's say, match. And this is something that we have never seen in the literature, and as I will show later, it paid off. Regarding the ground motion spectrum, we characterized it based on the 3 same categories. It's the Hessian phenomena that I said before: source, propagation, and site. For the source, we had to consider the same, let's say, source spectrum, because our inversion did not consider high magnitude events. So in order to maintain the causality of our ground motion simulation methods, we have to use source spectra that were, let's say, obtained for an event in the magnitude range of our interest. So for this, we took the ones proposed by Oth in his generalized inversion campaign, and we applied it to both of our cases. For the propagation, we do have a difference here. We have the results, attenuation functions obtained from the spectral inversion of both the Oth campaign found in the literature and the local data that we found. So here you can see the 2, let's say, sets of attenuation curves, which differ in 2 things: the reference distance, which is basically given by the distance, the closest distance from your observations to the source, and the associated estimated error. In the end, we used something like 356 events to conduct our generalized inversion technique, whereas Odd used 78,000. So his estimations are less subject to error, let's say. Finally, in terms of site, we considered for case A, which is literature-driven, transfer functions computed with Haskell method, matrix method, based on the soil profile for each of the stations of interest that we obtained from the Japanese network. And for case B, the one driven by our local data, we used the specific transfer functions that we obtained from this generalized inversion of our, let's say, observed data. And there are some important things to see here. For example, I'm showing here the comparison of transfer functions for both cases. For NIGH12, which is the station closest to the source at a distance of 18 kilometers, hypercentral distance, I'm showing here FKSH06, which is located at a distance of 68 kilometers, hypercentral distance of 68 kilometers from the source. And then you can see that you have, even though you have, let's say, similar amplitudes and behaviors, you have something that you are not able to capture, let's say, with the analytical model because of the simplification of the layered model of the site. And it's the shift of the amplification peak that you see for this structure. And it's something that will come up next. So remember that for this station, we have this difference. When we now go and looked into our results for our simulations, here I am presenting just one of the simulations that because in order to sample the variability, we conducted a whole campaign of simulations. So for each of the stations that I showed before, we generated a total of 100 simulations with a Monte Carlo sampling of each of the parameters that we had, let's say, identified from the literature and from our local data analysis. So let me explain you. I'm sorry, I failed here. I didn't put the legend. So you have here to the left, the station closest to the source, NIGH12. And you have here to the right, station FKSH06, which is furthest away from the source. You have in the first line, the observation from the observed reference event. You have in the second line, case A, and you have in this third line, case B. You have here in the titles of the columns, the respective components of each of the simulations. The ones that I'm presenting here correspond to the medium scenario obtained from the whole bunch of simulations that we generated. It was selected based on its energy, its RS intensity. And something that is very interesting to see here is that we are able to match, let's say, the maximum amplitude, the PGA of the simulations, but we're also to fairly match, specifically for case B and for the medium scenario, the shape and the duration of the ground motion, of the observed ground motion. Now, if we go on to look into significant duration, I'm here presenting the results of the comparison of the durations of our simulated ground motions the one predicted by the GMP, and the one from the observed reference event. And you can see that overall, they are pretty good. Of course, we use this model to calibrate it, but when you compare it with the observed reference event, you see that we have something that fairly, let's say, accommodates the durations that you see for our stations of interest. Now, when you look into the spectral content, which is what we use primarily to construct our simulated ground motions, you see important differences, and differences that are less evident from the study of other intensity measures, such as, for example, here. Remember that I said the peak here, the peak of the site effects driven by local study, the study of local data. It's something that we were able to capture with our study of local data, and it's something that we, let's say, attribute to a endemic phenomena that it was not able to be captured, again, let's say, by the analytical methods and the information available in the literature. If you go to the right and you look into the comparison of spectral amplitudes, something more, let's say, common for us engineers, you see that in this figure I am presenting here the comparison of the median for periods of vibration. You have PGA in the first, let's say, column, and you have 2 seconds. You see that our method, it's rather most efficient in representing the high frequency or low period content of the simulated ground motions, which is something that we know of stochastic ground motion simulation methods. They're very good to model the high frequency content, not so good to model the low frequency content, which is dictated by rupture and propagation phenomena. You see that also our uncertainty, which is presented here by 2 lines. You have a dashed line, which is given by the ergodic application of the COTA model developed for the area, and you have the solid line, which gives you the site-specific prediction from the same model. We were able to access the site-specific prediction because we were able to access the site-specific residuals used in the computation in the generation of the ground motion model. So we were able to compute and compare to this. And you see that our estimates are located somewhere in between. Of course, a more intelligent, let's say, sampling strategy would help us come closer to the site-specific, let's say, estimation of the ground motion movement. When you go to high periods, you see that the method is a bit biased. You are not very good in measuring what was observed, not so distant away, however, from what is predicted in the ground motion model that we use as reference. Regarding the uncertainty, however, we have larger uncertainty estimations when compared to both, let's say, applications of the ground motion prediction model. All right, that was the seismological validation. Yeah, seismological validation. Now I would like to present the civil building risk assessment, which is a work that we used to, let's see, evaluate the implementation of our simulated signals for engineering purposes. And basically what we did here was to compare the responses of suites of single degree of freedom systems to selected sets of hazard consistent records selected from a database of recording ground motions and a database of simulated ground motions. For this, we considered a realistic case study. We conducted PSHA at a site located in Perugia for rock sites. We used OpenQuake to run the hazard. We used Warren Atkinson's GMP to conduct the record selection. And we did so for a series of different hysteresis models, namely elastoplastic, elastic with strain hardening, and one with pinching. So basically, degradation of the stiffness. To be able to let's say, show the results in a better way, let me talk to you about the databases that we use to select records from. The reference database was a subset of the engineering strong motion database, and it was, let's say, limited to events with a magnitude between 4 and 8, high percentage of distances below 100, and a VS30 below 400. Our simulated database was constructed to match this statistical distributions so that our differences would be mainly attributed to the method and not to the availability of records in the database. Of course, both have the same number of records. You can see here a comparison of these, let's say, causative parameters and site parameters. You have here the distribution of magnitude and distance in violet, let's say, for the reference database, and in blue for the simulated database, and here the comparison of the sites that we used to model this. We further calibrated our database to match, let's say, the spectral content and areas intensity of groups, of different groups in our reference database. Here to see a comparison of the intensity measures that we looked at, let's say, to evaluate our database. And it's important to mention that we consider these two. We consider spectral acceleration at different periods of vibration, and we consider the areas intensity. We did not look much into the significant duration nor into the cumulative areas, cumulative absolute velocity. When we conduct record selection for these, let's say, suites of SUFs, we see that the distributions of causative parameters, site and scaling factors, fairly match between both of these databases, let's say. Here, I am using the same scale of colors. However, to present the information, I'm considering here a bar to delimit the percentile 16 and 84. The whiskers basically give you the distance between the minimum and the maximum observed, and the line, the horizontal line, gives you the median. When you looked into the comparison of intensity measure for the 10 intensity measure levels that we consider, we can see that we have a very good match in terms of the spectral content. And this is because we calibrated our database to match, let's say, this. We also see that in the areas intensity. However, when you looked into duration, you see that since we did not tackle this directly, you see some differences into the duration of our selected records. When you use these records to run nonlinear time history analysis of the SUFs that we defined before, and you compare the responses, something like this comes up. You see that there is an overall match of the responses of these structures to our records, our simulated records, and to those obtained from a recorded database, a database of recorded ground motions. When you go a step further and you go into the fragilities so as to be able to better observe the effect of the differences, well, the differences in these distributions of responses, you see that we have a rather good response for limit states of ductility equal 2, ductility equal 4, and ductility of 8, which we call collapse. When we go further into the damage level, let's say, when we go further into the non-linear range, we start noticing differences. And this is because of the period elongation. As I said before, our method is not very good to match the low frequency content or the high period content of the ground motions. So when you start experiencing damage and the behavior of your structure shifts, you start seeing some differences into our comparisons, let's say. Now, regarding conclusions and future work, well, this presentation introduced an improved 3D ground motion simulation method for structural response analysis, which is flexible, and it allows to propagate uncertainties in a very, let's say, rational way. It also comes up with a very low computational effort because you use simplifications for the wave propagation and rupture processes that are the most, let's say, complex. However, in terms of the disadvantages, it's still an approximation to a rather complex phenomena, which yields differences into some areas of the ground motion and some areas that might affect the response of structures of interest. Regarding the future work, the idea would be to work into the improvement of the P to S wave, the S to P wave model, let's say, by considering the estimation of vertical correlation matrix, which is not there, available, let's say, in the literature, and the definition of P-wave specific time-modulating functions, because the work from the 70s has mainly focused on SH waves. Furthermore, the idea would be to generalize this ray propagation, let's say, methodology into more complex cross-structure media, such as, for example, 2D and 3D propagation media. Thank you very much.
Thank you, Luis. Well, now, yes, questions from the audience. Don't be shy. I know we are all tired. Okay, Roberto. I was expecting one from you. I think your microphone is not on.
Okay.
Okay, now it's
Okay, so thank you very much. It is an interesting presentation. Probably the quality of figures could be improved a little bit because I missed some points. It may be also a problem of my eyes, but all in all.
Large screen also, it gets...
Yes, yes. Now, what I did not understand, okay, it is a stochastic approach where you try to input some physics of the phenomena. For example, for the case of Niigata, it was a magnitude, say, about 6.5 earthquake. And I did not understand precisely what are the physical characteristics of that earthquake that you have. I did not find anything about the slip distribution. There is no information about the slip distribution.
Yes. No, sorry, I didn't want to cut you. Go ahead.
Yes. The second is, you say that you have tuned the parameters to calibrate the duration.
Yes.
Okay, but these are tuned based on physical information or based on the record observation?
Okay, thank you very much. Those are very valid questions. In fact, because of the short length of the presentation, I was not able to fully describe the source model or anything else. But you can see here from this very, let's say, simple representation of the source that when we considered our, let's say, kinematic source model, the kinematic source model is used for basically two main purposes. One, the generation of the slip that is consistent with the seismic moment of the target event. And two, to model a more physical rupture. Usually stochastic models are coupled with, let's say, circumferential propagation of the rupture, where you have a constant velocity, and so you have a circle that basically that spreads into your rupture. Here we have a model. It's the model proposed by Francik Galovic, in which you have a rupture propagation velocity that is dependent on the properties of, at the depth of each point source. So you do have those physical input parameters there. You also have, let's say, the physics of the phenomenon by extrapolating or taking out the parameters that you use to generate your source spectrum, for example. So basically you study data and you obtain a parameter called stress drop that I don't have to explain to you, that you basically, it's a parameter, it's a variable that it's related to the physical, let's say, difference between the stress of the point source that you're analyzing before and after the rupture. So it's true, it's not a deterministic source model where you model each of these phenomena, let's say, rigorously, but you have a physical meaning to the parameters that you use to characterize the model. Regarding your second question, the duration, I am using here, since because the idea was not to model Niigata, Spanish, but the idea was to use Niigata as one of the observations that may happen for an event of the source. We use as target for calibration of the duration of the ground motion a GMP. So basically, we generated a, let's say, preset of simulations in which we generated ground motions with different combinations of parameters, sampled with LHS, and then we compared to the distributions of durations that we obtained from the GMP model, the valid GMP model for the region. And so in this way, you can check and select the ones that give you the distributions of significant durations that are closest to what you would expect from a statistical model in this case. But yeah, you could do the same for records that you have, let's say, registered at the area of interest.
Okay, let me just to clarify, try to clarify your answer. Typically, in the region that you have shown
yes.
in the one of your first slides, there is, okay, large magnitude, short distances where the records are sparse, you're typically in a situation of vicinity to the fault, okay, so near source situations. That situation, you may have typically short durations if you are very close to the source, and then the duration of the motion increases as you go far from the source.
Yes.
Then I'm wondering if these features are actually, say, input somehow in the model.
Yes, yes, for sure. The duration, the ground motion prediction equation that I used takes as input magnitude, distance, and several other, let's say, earthquake features, so that you have something that it's, let's say, consistent with your target scenario.
Okay, thank you.
Thank you very much.
Well, the evaluation committee hasn't finished deliberating yet, so any other questions? Paolo? Probably not a question, a remark.
It's more of a comment. One thing which I think Luis didn't have enough time to highlight also the quality of the lighting. It's kind of obliterates almost everything. But if we, as an engineer, let's say, forget about all the details for a second, at least for me as an end user of these ground motions. What's interesting here is that he generated a simulated ground motion data set with 7,000 ground motions, three components, exactly to mirror one that had a real ground motion for this, with the same magnitude, same distance, same soil conditions. When you use these two data sets and you use a conditional spectrum to select the ground motion that others are consistent, and then you provide and you compute fragility curves, et cetera, you get pretty much identical responses. So from that's what an engineer would like to see. So I may not be able to understand all the details, but this is just the end of the journey. There are other checks, other sanity checks in between, which we did. But that's encouraging. That's encouraging because that means that nobody will ever consider to completely replace real ground motion with a simulated ground motion yet. But at least now we could maybe integrate the real ground motion with simulated ground motions whenever it's needed, and somewhat use confidently the results. This comparison that you showed is really extreme, right? So because we only use real ground motion or only use simulated ground motions, and the results are encouraging. So that's, from an engineering point of view, I think it's an important finding. Thank you.
Thank you, Paolo.
Any other question? I would have just one question, Luis, on the single building risk assessment, on the case study part. I was just wondering why was the choice made for the use of equivalent single degree of freedom systems? I can imagine it has to do with you being able to test it over a large number of structures. My question was just because usually there's criticism towards equivalent single degree of freedom systems precisely related to the fact that they usually cannot capture the full content of the records or the impact of the content of the records as a 3D structure would, or a fully modeled structure. So I was just wondering if you thought a little bit about this, and how much do you think this can impact the results?
Sure. So basically, the idea to go to SUFs it's founded on many reasons. One of them being that it's, let's say, pretty much standard practice for first step, let's say, validations. Second, we were dealing with a lot of simulations. We were dealing with a large number of nonlinear time history analysis. And in order to be able to, let's say, evaluate different hysteresis models, different periods of vibration, also periods of vibration that are not within the range of, let's say, functionality, let's say, representativeness of our method. So we went for that. Also, if you use SUFs, your response depends on just one, let's say, exactly, as you have. And so if you see something, if something is out there, it will be shown there, and it will be highlighted, let's say, because it's just one single degree of freedom. There's no, let's say, repetition of forces or, yeah. Yep.
Thank you. Okay, I think we will then close this session and wait just for the final results of the evaluation committee for the first 3 candidates, for whomever wants to wait for us. In the meantime, thank you very much, Luis. And for those that are leaving now, so we will be having the dinner of the seminar here in the church at 8 p.m. more or less. Okay, so see you in a while.
Grazie a voi.